Okay, so hi everyone, good morning, and welcome to the 2022 meeting of the Atmospheric Chemistry Special Interest Group of the Royal Meteorological Society. So for those of you that don't know me, I'm Ryan Hussaini from Lancaster University, and on behalf of myself and Paul Griffiths from Cambridge, welcome, great to have you here. So the theme of this year's meeting is Atmospheric Chemistry and Data Science, the Final Frontier. And I'm sure you will all have seen in recent years, there's been a huge flurry of activity, studies looking to try and leverage the power of machine learning, of advanced statistical methods, of data science more generally, and apply it to better understand topical issues in atmospheric science around air quality and climate. And we're going to hear today from a range of speakers who will tell us a bit about method development and also about application and how data science is having a transformative impact on our understanding of some of these areas. Okay, next slide, please. So just a few housekeeping things. First of all, before we begin, if you haven't heard of the Met Matters newsletter by the Royal Meteorological Society, please consider signing up to it to keep informed about weather and climate related content. Next slide, please. And if you're not a Royal Meteorological Society member, then again, please consider joining because of these benefits and perks that are shown on this slide. Okay, so final slide. I'll hand over to Paul in a moment. We have two sessions. The morning session, we have 4 speakers running from 11 till 12:30, and then the afternoon session runs from 2 till 3:30 GMT. If you could please pop questions for our speakers in the chat, Paul and I will endeavour to read them out after the speakers have finished. So I'll hand over to Paul now, and thank you everyone again for joining.
Yeah, good morning everybody, and can I have my own note of welcome and also sincere thanks to the Royal Meteorological Society staff, Catherine and Hayley, for their help in putting this meeting on. Thanks to you both. We've got 4 speakers this morning. It'd be most helpful for us if you put your questions in the Q&A session. We can keep an eye on that as well, but feel free to use chat or Q&A. Q&A is best. Lily, if you'd like to share your screen.
I'll just do that now. Share. Hopefully they're sharing. I'll just make them full screen.
We can see your slides.
Yeah, and then, is that okay?
That looks good, thank you. The floor is yours.
Hi everyone, I'll just introduce myself. I'm a final year PhD student at Lancaster University, and my general research area for my PhD has been using data science methods to model UK ozone concentrations. And the work that I'll be presenting today is on downscaling an atmospheric chemistry transport model ozone surface using machine learning. Here's the outline for my presentation. I'll start by giving a brief introduction into surface ozone, what it is and why we should care about it. Then I'll talk about the specific atmospheric chemistry transport model ozone surface that I've downscaled. I'll run through the data that I've used in the downscaling process, followed by the specific method and machine learning model. And then finally, I'll present some of the analysis that I've done using the downscale surface, and also touch on the differences between the downscale surface and the original. Okay, so I'll start by giving the introduction into surface level ozone. Ozone at the surface level is an air pollutant. It's actually a secondary pollutant, meaning that it's not directly emitted. And it's made up of the precursor pollutants, NOx and VOCs, in the presence of sunlight. Concentrations of ozone are typically highest in spring and summer for the UK and in rural areas. Ozone is a key component of smog, and actually a few days ago, it was the 70th anniversary of one of the most famous smog events, the Great London Smog of 1952. In which an estimated 4,000 people died from exposure to the toxic air. As a result of this, a series of laws called the Clean Air Acts were introduced to avoid this happening again, and surface level ozone is still one of the regulated air pollutants for the UK. Exposure to high levels of ozone can lead to various health problems, such as inflammation of the airways. It can aggravate lung diseases such as asthma, and in severe cases, it can even lead to death. Ozone doesn't only affect human health, it's also damaging to plants as it can interfere with photosynthesis, it can reduce crop yields, and it can make plants more susceptible to diseases. As part of the regulating of ozone concentrations, measurements are taken at stations dotted around the UK. However, if we want to learn more about ozone concentrations at places where measurements aren't taken, it can be useful to use atmospheric chemistry transport models that predict air pollutant concentrations across the surface. The particular atmospheric chemistry transport model ozone surface that I've been working with is from the EMET4 UK model. The EMET4 UK model is the UK version of the European Monitoring and Evaluation Programme Unified Model, EMEP. And the version that I've downscaled is on a 5x5 kilometre resolution. And the model itself is used by DEFRA to determine the impacts of various policy decision scenarios on a number of different pollutants. I've downscaled data for 2001 to 2018, and I've done this for MDA8 ozone, where MDA8 ozone is the daily maximum of an 8-hour running mean of ozone concentrations, and it's commonly what's used in ozone analysis. I used quite a lot of data in the downscaling process, which included ozone measurements that are available in the open air package in R. The measurement stations that I used are shown in this map on the slide, along with how many years of data I was able to get from each measurement station. I also used the EMET4 UK ozone surface, various meteorological variables from WRF that are known to drive ozone formation and transportation, location-based variables, which included distances to different types of roads, as ozone concentrations are typically lower at roadside locations. I also used temporal variables such as year and month, and these were included to capture any seasonal or long-term trends not already picked up in the EMET4 UK ozone surface. So my first bit of work to do this was finding out how the original EMET4 UK surface compares to the measurement ozone data. And this figure is showing a percentile plot comparing the percentiles between the two data sets, with measured ozone on the x-axis and the modelled ozone from EMET on the y-axis. And what this figure is showing is that EMET4 UK ozone is biased high compared to the measurement data. And we believe that this high bias is due to the coarse resolution, in that it isn't able to pick up on the lower concentrations of ozone that's found in towns and cities that happens due to NOx titration. And this is why we then decided we would downscale the ozone surface. A high resolution ozone surface is particularly useful when wanting to consider health impacts of ozone and exposure levels. The specific downscaling method that I used was made up of 3 main steps. The first step was to regrid the EMET4 UK ozone surface to a higher resolution of 1 by 1 kilometres. Then I needed to train a machine learning model to predict measurement ozone, and this was done using the 1 by 1 kilometre EMET ozone surface as a predictor variable, along with other variables known to influence ozone formation and transportation. And then the final step was to use the trained model to predict a 1 by 1 kilometre gridded ozone surface. The specific machine learning model that I used was a gradient boosted tree, which is an ensemble model that's made up of lots of decision trees. The decision trees are produced sequentially, and each tree is trained on the errors from the previous tree. All of the trees are then combined together using an additive model, and the weights for each tree in the additive model are estimated by the gradient descent procedure. Python has a very optimized implementation of this algorithm called XGBoost, which is widely used in the machine learning community for regression and classification tasks. And this is the package that I used for this project. There are several advantages to using a gradient boosted tree. Firstly, it can model nonlinear relationships between lots of different features. It's very efficient, especially when using the highly optimized Python package implementation of it. You can also apply what's called an explainer model to understand the feature importances, as in what variables are driving the ozone predictions. But there are some disadvantages to using this particular model. It requires significant parameter tuning in order to get a good result. It can be prone to overfitting to training data. However, there are terms in the package that try to control the model complexity to reduce the tendency to overfit. And it's also sensitive to outliers in the data. In order to apply the gradient boosting tree to predict ozone concentrations, I had to decide what would be the best objective and evaluation functions for the model. As the measurement ozone data is long-tailed, I used a gamma regression in the objective and evaluation functions. And this gamma regression is suited to modeling continuous, non-negative and long-tail data, which is what the ozone measurements are. And using the gamma regression within the model allowed it to capture the high ozone events much better. As with most machine learning tasks, there's a need to balance the fit of the model to data that it's seen and what it's been trained on, while also still having a generalizable model that can predict for situations that it hasn't been trained on. To make sure that the model was fitted in a balanced way, I performed 2 standard machine learning evaluation tests. The first one was done by splitting the data into 70% training and 30% testing. And the second one was a cross-validation test, which involves splitting the 198 measurement stations into 10 groups of roughly the same size, training the machine learning model on 9 out of the 10 groups, and then predicting the ozone concentrations at the unseen group of sites. And then repeating this test until every group of sites had had a go at being the unseen site. Whilst doing this, I could produce a model that scored very highly in the 70-30 test, but then it wasn't able to predict ozone at measurement locations that it hadn't seen before, so it wasn't generalizable enough. The final trained model that I ended up using to create the downscaled surface had these R² and root-mean square error results for the 2 evaluation tests. And we felt that these results were a good balance between being able to reproduce measurement behavior at a location that the model has seen some data for, while also being able to predict ozone at a location the model hadn't seen before. After I was happy with the training of the machine learning model, I then used it to create the 1 by 1 kilometre gridded downscale surface of ozone for 2001 to 2018. And here's an example of how that surface compares to the coarser 5 by 5 kilometre EMEP surface. The original EMEP surface has roughly 10,000 cells, whereas the new downscale surface has roughly 230,000 cells. So it's far more high resolution. I then evaluated the downscale surface in the same way that I compared the EMEP4 UK surface against the measurements, by taking the nearest cell from each gridded product to each measurement station and matching them up. I found that by downscaling the EMEP4 UK surface, it improved the R² result by 128% and reduced the root-mean square error by 37% when compared to the measurement data. The figure on this slide is similar to the figure that I showed earlier, the percentile plots, with the downscale percentiles this time in green and the original percentiles in orange. And the downscale surface better represents the measurement ozone by following the 1-to-1 line more closely. As I mentioned on an earlier slide, a benefit to the specific machine learning model that I used is that an explainer model can be applied to it to find out what was driving the prediction of the ozone concentrations. And this figure was created using SHAP, which is short for Shapley Additive Explanations. And SHAP is a model that can be used to explain the outputs of a machine learning model. What this figure is showing is each of the predictive variables used to train the machine learning model to predict the ozone concentrations, and it's ordered them in terms of importance. So the most important predictor is at the top, and the least important predictor is at the bottom. The EMEP4 UK ozone came out as the most important feature overall for predicting ozone concentrations, which is sensible as it already is an ozone concentration in itself. Daily maximum temperature is the most important meteorological driver, and distance to road type 1, which is motorways, is the most important location-based variable. As well as being able to determine the overall most important features, SHAP can also be used to determine the impact on the model prediction, as in does it lead to a high prediction of ozone or a low prediction based upon the individual feature value. For the left-hand side of this figure, each dot represents predicting a single day's ozone concentration, where the colour of the dot is based on the value of the feature, and the position of the dot determines the impact on the model output. If the dot is placed towards the right, it's contributing to a high prediction of ozone, and if it's to the left, it's contributing to a lower prediction of ozone. And so if I look at one of the features as an example, daily maximum temperature, T2, which is the second feature down, a high daily maximum temperature, so the dots that are coloured in red, are towards the right of the plot, which then leads to high ozone predictions, and low daily maximum temperatures, coloured in blue, are leading to lower ozone predictions, which is what we'd expect. One of the main reasons that we created the downscale surface was to have a better estimate of exposure to health threshold exceeding levels of ozone. The UK government defines a moderate health threshold level of ozone as 100 micrograms per metres cubed and has an objective to not exceed this level more than 10 times in a year. This figure is showing the importance in correcting the high bias in the EMET4 UK ozone surface when it comes to estimating health threshold exceedance days. What it's showing is the 2014 to 2018 average number of days above the moderate health threshold level for the UK. And there's a considerable difference between the two data sets in the estimate of the average number of days above this moderate health threshold level. Using the downscale surface, we find that 27% of the UK is failing the government objective in exceeding the moderate health threshold level more than 10 times per year, whereas the EMET4 UK estimates that almost all of the UK is failing the government objective at 99%, which is quite a different result. I've also looked at the trend over time in high-level ozone from each data product that I had, the EMET4 UK surface, the new downscale surface, and the measurement data. I found that 90th percentile ozone is decreasing in all three of the data products over 2001 to 2018 and for all regions, although the largest decreases are seen in the south of the UK in the two gridded products. Particularly, the region with the largest decreasing trend is the east of England in the EMET surface and the southeast of England in the downscaled surface. Quite a different picture is seen when only considering measurement ozone. However, the measurement network is quite sparse in places and doesn't necessarily reflect the general behaviour of an entire region. Northeast England actually comes out as the region with the largest decreasing trends in the measurements. However, this estimate is only calculated from 4 measurement stations, compared to the far larger samples from every region in the gridded data products. I've also considered trends over time in exceedances of the moderate health threshold level of ozone. The moderate health threshold level is 100 micrograms per metres cubed. As I mentioned before, the UK government tries to not exceed this level more than 10 times in a year. Due to the high bias in the EMET surface, it estimates that the 2001 to 2018 average percentage of the UK failing the government objective is very high at 96%, whereas the measurement and downscaled estimates are much lower at less than half of the UK. I also calculated the trends of the amount of the UK failing the government objective and found that the percentage of the UK failing the government objective is falling in all 3 data sets. However, this was only significant in the downscaled surface. As a particular example of the differences between the downscaled and EMET4 UK surfaces, the figure on the right is showing the number of moderate health threshold exceedance days for the heatwave years 2003 along the top, 2006 and 2018 at the bottom, along with the corresponding mean temperatures for each year. For a cell in the surface to be passing the government objective, it has to be coloured yellow in the colour scale that I've chosen. as this means that it has exceeded the threshold less than 10 times in that year. And this figure is showing that 2018 has far more yellow coloured cells in the downscale surface than 2003 and 2006, suggesting an improved picture of health threshold exceedances for the UK in heatwave years. The final results that I wanted to present are from a NOx reduction scenario analysis, which we considered in order to determine how reducing UK NOx emissions, which is a precursor to ozone, will affect ozone levels for the UK. The 3 NOx reduction scenarios were reductions of 20%, 40% and 80% of UK NOx emissions, and these were run for the year 2018. The results of all of these NOx scenarios are compared against a business as usual 2018 with no NOx reductions. All of these scenarios were run using the EMET4 UK model, and then the outputted surfaces were downscaled using the same downscaling model presented earlier, with the assumption that the same downscaling would hold in these scenarios. And here are the results from the NOx scenario analysis. The left columns in this figure show the results from a 20% NOx reduction. The middle column is for a 40% reduction, and the right is for an 80% reduction. Each cell in the maps are coloured based on the difference between the scenario run and a base run of 2018 with no NOx reductions. And I focused my analysis on 3 statistics of ozone: whole year mean, which is the top row in the figure, March to August mean in the middle, so that's spring and summer ozone, and 90th percentile ozone, which is the bottom row of maps. I found that NOx reductions of 20% and 40% lead to increased ozone concentrations for large portions of the UK, whereas severe NOx reductions of 80% lead to decreased March to August and 90th percentile ozone for a lot of the UK, although the whole year mean ozone is still increased for a lot of England in the 80% NOx reduction scenario. In all 3 scenarios, the areas most affected by increasing ozone were highly urban areas. However, as this analysis was done for only 1 year, I think an interesting extension to this work would be to see how concentrations of ozone are affected over a longer term. In summary, machine learning can be a useful post-processing tool for atmospheric chemistry transport models, whether it's to downscale a surface output or to bias correct, or even both. Running a chemistry transport model at a high resolution can be really computationally expensive in comparison to a method like this. The downscale surface better represents measurement behaviour, which is particularly important when considering the impact of high-level ozone and health threshold exceedances. I found that high-level ozone is reducing across the UK, and I found this result in all 3 of the data products that I looked at. And the final point that I wanted to share is that we need to consider how NOx reductions will impact ozone concentrations, as NOx reductions can, at least in the short term, increase ozone concentrations for large parts of the UK, especially in towns and cities, which is where a lot of people live. And so it's an important thing to consider. Thank you for listening, and I'm very happy to answer any questions.
Thank you so much, Lily. Incredibly comprehensive overview. Maybe I could ask the first question and ask if you've considered extending the change in ozone to include the population that is exposed. So you could do a kind of where is the ozone changing, where people live, that kind of analysis. Is that a possibility with your data?
It definitely is. You could even, so you could use population indexes as a predictor for the ozone concentrations. To create the downscale surface as well.
Thank you. There are a bunch of questions in the chat. First one, I think, reflects the high quality of the figures that you've presented and asks, are you using OpenAir to plot all the map figures in your study? A technical question there. No, I'm not actually. It's using Xarray in Python to produce the maps. That's for the cell shaded maps. And then the ones which are the regional summaries, the shape files, that was done using GeoPandas and Matplotlib. Thank you. Sandit Donza asks, did you check how EMEP observation ozone differences are related to NOx emissions used in the model? I guess a question about systematic bias in the EMEP model.
No, we didn't, as we only had access to the ozone surfaces. But the reason why we didn't include NOx in the downscaling model to begin with, or at least the EMEP NOx, is because we thought that the biases present in the EMEP surface would be as a direct result of their NOx output.
Okay, thank you. Zongbo from Birmingham says, great talk, Lily. Can you expand on how NOx reduction changes the exceedances of ozone across the UK?
So this is the NOx scenario analysis. We focus more on just, is it going to generally increase or generally decrease, as it's quite an extrapolation to use the same downscaling model in that scenario. So we can't necessarily trust a prediction of an exceedance of an exact level.
Yeah, because you're using a pre-trained model from a slightly different data set.
Yes, exactly.
Thank you. And Doug Finch asks, can you get a metric of confidence from the machine learning model? By which he means, could you have a map of confidence of prediction per grid cell for the downscale maps to see any areas where the model may struggle?
I'm not sure you could get it per grid cell. The only way that you could get the spatial confidence would be how confident you are at each measurement location, as that's the only thing that we know.
Okay, if there are no more questions, and I don't see any, I will say thank you again, Lily, for an excellent talk, and invite our next speaker, Doug, to take the floor. Thank you. Stop sharing as well, that would be great. Thank you.
Great, thanks. I'll share my screen. Hopefully you can see those slides all right.
That's great, thank you.
Great, well, thank you very much for inviting me along to this talk. I'm going to chat a bit about what we're doing up at the University of Edinburgh with myself and Professor Paul Palmer. As the title suggests, we're sort of making an automatic image detection to find pollution sources from satellite data. And I will say now, apologies if we get a soundtrack to this talk. My upstairs neighbour is starting to learn the piano today, and it's sporadic noise coming through the ceiling, but hopefully we'll be all right. So to put this in a bit of context, we started with a very big question, which is trying to quantify greenhouse gas emissions, specifically CO2 emissions to start with. And as we all know, there's an urgent need to reduce greenhouse gas emissions. This was exemplified with the recent COP summits. But to be able to sort of to aim to reduce the greenhouse gas emissions, we need to think about how we monitor, report, and verify emissions to comply with the COP aims. And we need to do that globally and on lots of different scales. So currently, we have emission estimates for countries, smaller regions, but on really pinpoint scales to say individual cities or power stations, we need to sort of focus in on these hotspots. And we also need to know, say, a new power station is being built, are they being changed, decommissioned, etc., as time goes on. However, looking at CO2 by satellite is pretty difficult. It's a very homogeneous gas relatively across the globe. It's difficult to detect hotspots, and it's difficult to separate anthropogenic CO2 from biogenic fluxes. So any sort of forest or farmland, etc., CO2 exchanges going on. So instead, we sort of shifted our focus a little bit to say, okay, we can look at co-emitted species from CO2. It's, say, for example, nitrogen dioxide or carbon monoxide. And can we locate hotspots from here and then determine emissions from these gases, and how does that affect CO2? So it's our sort of big goal we started off with. And then we thought, well, while we're at it, what other species of pollutants can we look from space? So what about SO2? You know, can we easily detect hotspots from volcanoes or other industrial processes, say coal mining, etc.? And also, can we use locations of observations of NO2 and the co-located measurements of formaldehyde, and that might be able to extract information about the photochemical environment from a particular hotspot, and that might feed into sort of ozone production, a bit like what Lily was talking about just now. And also, is it possible to directly observe methane as well? Would the individual plumes of this stand out from the background? This would be a lot more difficult than something like NO2 or SO2. So something key with NO2 and SO2 is their short-lived atmospheric lifetimes. So when you see a high concentration of these species, the likelihood is the emission source is very close to that high concentration. So there's a very easy direct link between the two. So this is our sort of overall goal. Is this achievable? Can we develop a new way of finding these hotspots using machine learning from satellite data? So the satellite data we're using is the Tropomi instrument on top of the Sentinel 5P satellite, which I don't know how many people are familiar with this satellite, but so Tropomi stands for Tropospheric Monitoring Instrument, which observes a number of trace gases, including nitrogen dioxide, but other ones as well, so SO2, methane, etc. It was launched back in 2017. We have data from spring 2018 up to present day. Hopefully it lasts for a few more years yet. And it's a relatively high resolution satellite for atmospheric sciences. So each pixel the satellite gives is about 5 by 3.5 kilometers. This does change a little bit depending on the species, but for the ones we're looking at, that's the resolution. And each swath that goes around the Earth, like it shows in this animation, is 2,600 kilometers wide. So we get a full global coverage within a day, pretty much. It has a local overpass time around lunchtime, so it should be heading over Edinburgh if it clears up in about an hour and a half. Yeah. This is a instrument we'll see later. It is affected, or sensitive I should say, to cloud cover and light. It needs sunlight to operate fully, and in wintertime in the northern hemispheres and southern hemispheres as well as cloudy areas, this does restrict data, but well, it's something we have to deal with, unfortunately. So in terms of finding plumes, as I say, we're going to use this instrument to observe nitrogen dioxide, sulfur dioxide, methane and formaldehyde. It doesn't have other species. For now we're focusing on them. We want to pinpoint the emission surfaces, so we want to know when and where these emissions are occurring, and hopefully with that we can start building up a database which is as up to date as the satellite files are available, if that makes sense. And we want to do this by looking at individual satellite the daily files. So although this map is an example of NO2 column, this is actually the mean over a year. We're looking at an individual swath at a time. This Tropomi instrument produces over 6 gigabytes of observations for each species per day, so it's an awful lot to look through. So we think this is a perfect task for automation, which is why we moved to machine learning. So what exactly are we looking for? So these plumes we're after, they're sort of a long cloud of pollution spreading out from a single point of origin. A classic example being a smokestack, like in this image here from a power station. You could also get a lot larger plumes from combined sources, such as a city. And from above in the satellite data, they look like these 3 examples here, where the yellow sort of smear across is the plume shape, and we will assume that the maximum concentration is the center of the plume, the emission source. So we want to look at these through our data, in our data. So we want to use machine learning to detect these. So what we did is we trained up a cognitive neural network, which is the same principle as any image recognition model. So you do face recognition or text recognition. We pass the model an image, which is just a subsection of the satellite data, and want it to say whether there is a plume or not. So we're using the Google's TensorFlow, specifically the sort of sub-Keras package with this, which is open source Python module, so all the code can be reproduced. However, it is a bit of a black box, which is a limit to machine learning. methods, but I won't go into that at the moment. So we create this convolutional neural network with a load of trained model images of what we want it to find, these example plumes, tested it with our images, and then pass the model to unseen data to see what it can pick out. I won't go into the architecture of our model, but basically we have these two sections of a convolutional neural network. There's the convolution side, which is these layers and layers of image processing, basically, which pulls out different features in an image, and it quickly gets beyond features that are really comprehensible to humans but might mean something to a computer. And then once these features have been sort of pulled out, they're flattened into a single dimension array and fed into a neural network which picks out the importance of these features and says, okay, this feature keeps reoccurring, therefore this is a plume, or these features are not important, it's not a plume, etc. And all that gets fed into a single true or false, there is a plume in this image or not. So the data we used, we needed examples of both plumes, nice plumes, so like this image at the top, also no plumes, I guess the image at the bottom, and confusing ones like the middle one. This is based on my judgment of what a plume is, which is probably a source of error. But I created a label database of over 6,000 images, half of which have a plume, half of which I think don't have a plume. And I basically went through Tropomi data one by one, picking out plumes. It was a very tedious task, but we have a good database in the end. So all these images are examples from all across the globe at all times of year. We don't anticipate that that would have much effect, but it's good to have a good range. Skipped over the oceans because I don't want to go through lots of basically empty tiles. And then we randomly split the data into 8% to train the model, and we kept 20% aside to test to see how well the model will perform. I did try crowdsourcing this briefly. It's fairly unsuccessful. I can talk about that later if there's time. So a lot of, as I say, all this is based on my judgment. On what is a plume or not, I think people would disagree. So the model is never going to be perfect because human judgment is never going to be perfect. But we ran this through the model, and with our configuration, we got about a 92% accuracy on plume detection based on our test images. So we were pretty happy to proceed with this. So our next step was to put a swath into the machine learning model. So this is an example swath from one day of Tropomi data, and the little yellow box is showing we take these images and we do 28 by 28 pixels. We split the swath into and scan through it and feed it through the model. And at some point, the model says, yes, there is a plume here. So in this location, it said, yes, there's one just off the coast of Brazil. And then we take the maximum value of that, and we can extract the latitude and longitude and time from that. And I just had a quick look on this example on Google Maps and put it in, and it hovers right over this. I'm not quite sure what it is. It's a facility. There's obviously some chimneys in the background, some fuel tanks. So it's highly likely that this is some sort of combustion happening here, power station, refining process, something. It's important to note, though, each pixel is, as I said, 3.5 by 5 kilometers large. Now, this is plenty big enough to include multiple sources in one pixel. We are restrained by the size of the data, the resolution here. So although this may be contributing towards the plume, it might not be the sole reason. And places like a city, it could easily, include an awful lot of industry and motor transport, etc. But this model is performing pretty well by itself. So we want to apply this to a larger data set. And here's an example. So just the sheer amount of data we have to go through, and why machine learning is ideal for this. If we take 12 months of data, obviously we have 365 days. For each day, we have about 14 of those swaths per day, which in each of those swaths is an individual tile. So for a whole month, we've got over 5,000, a whole year, we have over 5,000 files, which is over a terabyte of data. And then we break our swath up into these 28 by 28 pixel images. And the reason we choose that is there's a nice balance between small enough that the model can perform accurately and quickly, but large enough that hopefully it can incorporate most plumes from decent sources. So we're talking about a 400 kilometer-ish image here, basically. So each swath has 1,776 images in it, which, although it doesn't fit nicely within a swath, that's how many we extract, which is over 9 million images per year of data per species. And we're extending this to ideally all available data for all species, so we'll end up with a heck of a lot of images. We do filter these images with a quality control before they're fed into the model, so it does reduce how much is had to process by over half, but it's still an awful lot of images to go through. So if we start looking at some results, I'll first show NO2. So there's a few things before these maps look a bit overwhelming. So we're showing all NO2 plumes found by our model between June 2018 and June 2020. This is what we ran the model on initially, these two years of data. We found over 200,000 plumes where the model has more than 75% confidence that there is a plume in the image. Now this looks totally saturated because on this map the individual dots are a lot bigger than a tropomi pixel, but we'll zoom in a minute and see some features. But there's some points here to pick out. Firstly, we've crudely, admittedly, split the anthropogenic and the biomass burning plumes by co-locating any plumes that our model found with biomass burning data from the VIIRS data set. So that's a daily high resolution fire data set over the globe. And we simply say, does our plume co-locate with this fire? Then it's probably biomass burning. It's going to miss some, it's not going to be accurate in some, but for the time being, we separate those two. And this is where we only focus on anthropogenic combustion. So these plumes have no idea initially, but they're not given any information about where they might be found, but we're starting to pick out interesting information. I mean, they're sort of in the usual suspects over developed countries, etc. you'd expect, but there's also picking out ship tracks, which we weren't expecting, which was a nice little bonus. And as well as, so say if you look in northern Alaska, there's a lot of coal mining, oil extraction up there. It's picking out hotspots from there, which previously are difficult to see because the scale of them has you've not been able to pull them out in traditional hotspots methods because the scale of them has been a bit too small. But if we zoom in a little bit, so we've got two maps here. There's Europe on the left and the Gulf on the right, and the blue dots are showing where the NO2 plumes are. I've circled major cities in grey. Any power stations from the Global Power Plant Database are in red, and known flaring regions are in orange. So there's a few points here. I guess, firstly, a lot of the places we'd expect plumes are major cities, Paris, Madrid, London, Milan, etc. We see clusters of plumes. And there is definitely a lot of noise in this, but we can have confidence the more clustering there is, the more likely there is that there is definitely an emission source there. We're also seeing the ship tracks through the Gibraltar Strait, which is a really nice little thing we weren't expecting. But also, this highlights, so the power plant station, so the global power plant database that we used is not ideal. It's decent, but there are known errors in it. For instance, it's a bit hard to see on this map, but if you look up near where I am, near Edinburgh, there's a power plant supposedly located on a RSPB reserve island just off the coast of Edinburgh, where in actual fact it's a lot further inland. So we're just totally missing that. We see plumes over where the power station is. The power station database is mislocated. And that's just one I know about because I live nearby. There are all these others across the world, which I have no idea on accuracy. We're also not getting a huge amount of flaring, especially in the North Sea. This might be issues to do with tropomi collecting data over water. There's also issues with the flaring databases. This is detected from nighttime flaring. Tropomi goes over at midday. So if flaring isn't occurring at the same time, then we're not going to pick it up. But if we look over the Gulf, we get some flaring regions. We get a lot of the industry. We get the Suez Canal and cities as well. If we move on to SO2, so we ran exactly the same model for SO2. Now this shows a lot more noise. We found a lot fewer plumes. So we found about a tenth the amount of plumes, 21,000-ish, which is to be expected because there's probably fewer hotspots of SO2 than there are NO2 in the world. Again, this image is saturated because the pixel size the tropomi pixel size is smaller than the dot on the image. but we're seeing clustering around known locations. And again, I'll zoom in a moment. There's a lot of noise over Canada and Alaska. I've recently found out this is to do with the way the data from the satellite is processed before given to the user, but this is currently being fixed, and people have shown a lot nicer ways of cleaning up data and don't know what the word is, sort of false results, if you will. So it cleans it up nicely. So hopefully that will impact our results. So this is sort of a work in progress and needs to be refined massively still. But again, we're seeing clustering and confidence about what we're seeing. So here over Central America, we've got multiple volcanoes it's picking out, but as well as off and onshore oil fields and refineries, they're being picked out. And again, it's giving us confidence that our method is working nicely. And as well as the volcanoes, we're picking out a lot of industry that are giving off massive amounts of SO2. So again, looking in the Gulf, we've got a lot of oil refineries in Q8. Interestingly, in the top right-hand corner, there's SO2 plumes being found in Turkmenistan in what's called the Mary oil field. And this is a known area of a lot of CH4 leaks. So there's potential there for some interesting co-location of measurements and what that might tell us about emission ratios and etc. So we have all this data, and if you really want, we have 2 websites with this later on, so you can zoom in and pan about and look. I spent a long time sort of aligning these, or zooming in on a cluster and finding a power station in the middle of the Atacama Desert or something. So there's our NO2 plume website, the address up there. I'll put it up again later. And our SO2 plume website. These will be merged at one point, but currently they're 2 separate projects, or 2 different websites. And we've also put on the SO2 plume websites known places of copper smelters, and there's quite a few SO2 plumes, like in Australia, that coincide with copper smelters. So, yeah, it's a lot of fun to play with that if you'd like to have a go. And hopefully, well, this will be constantly updated as we refine this. As I say, it's a sort of a work in progress, really. The NO2 work started off as a little sort of, can we do this? And then we've got a bit more funding from ESA to look into the other species. And that's only really just got going. So it's going to be tweaked and improved and constantly updated with new data. Unfortunately, I don't have anything at the moment to show the eruption of Mauna Loa, just because I've not got time to look around at it yet. If we look at this potential data, or the potential of this data for looking at co-locations with other satellites. Here I've got an example of a plume that was found over Buenos Aires, and it coincided with the pass of the OCO2, which is observing, which way around is it? I think Observing Carbon Observatory 2, so CO2 measurements. It passed over Buenos Aires on the same day, over the same location of this, what we'd call the centre of our plume. And although we've not done anything with this information yet, it shows you sort of an example of potential narrowing down of the information we might need to process to get some interesting results to do with emission ratios, etc. So we can look at this coincident measurements. The stripe of orange is the OCO2 overpass, and that's the entire swath of the OCO2 overpass, where that purple square is about 1/16 of the entire swath of Tropomi. So you can just see the different scales of satellites. It's huge. So as we get more data and put in other satellites, hopefully we'll be able to improve these coincident passes and start to extract information and statistics about these, which could yield some interesting results. So in conclusion, we've shown that neural network, our initial studies, is a really useful tool for helping to process these huge amounts of data. We've successfully located NO2 and SO2 emissions globally, some major sources of them. We have done some comparisons against known data sets, and we've performed pretty well. Obviously, there is refinements to be made. This is still a very rough outline, but it's still exciting to show what we can do. And it's going to become more and more useful with more and more data. So each day more data comes in, we get a longer time series. And when we're going to combine this information with other data from either other satellites or from the same satellite, we can start to infer emissions on a really rapid timescale. And we can go back to our initial question, which is, can we get very quick, very precisely located emission estimates based on satellite data. The first lot of this was put into a paper if you're interested to read up a bit more about the NO2 plumes. As I say, we're now moving on to improving this model and using SO2 plumes, etc. So with that, I'll stop and thank you very much for listening. And if you'd like to go and have a play around the maps, the zoomable maps, hopefully those two websites will work, although I will say the caveat, I'm no web designer, so they're not perfect websites by any means, but thanks.
Thank you, Doug. Who doesn't like maps? I shall be on that website when I'm eating my sandwich at lunchtime. I wonder if I could ask if there's the potential to validate emissions inventories. Particularly, I'm thinking SO2. Maybe NO2 is rather hard from a not very, you get the column. I wonder if it's possible to kind of infer SO2 emission strengths.
Yes, definitely. And we're at the moment looking, so as I say, we're at the beginning of this project, but part of this project is to look at use cases for this kind of data. And validating current emission data sets is definitely on the list. Yeah, and we can hopefully see anything that is changing rapidly or is just wrong to start with, not located correctly, etc. With SO2, I think it could be really, I think that's kind of a low-hanging fruit with this one because there's very nice point sources, volcanoes, etc., which should be a lot easier to process. But yeah, there's definitely a lot of potential for this.
Zongbo asked a similar question, which is whether you see changes in the emissions over time, I guess trends in the emissions. For example, he says along shipping lanes.
Honestly, I don't know yet. We're hoping that's one of the things to do. So the NO2 data I showed with the shipping lanes is 2 years of data. I've now just downloaded everything from spring 2008 to last week, I think. And we're going to run all that, run the NO2 through it, and then we will hopefully be able to get some nice time series data. One thing I really would be interested in seeing is, do we see any difference with the Ever Given ship blocking the Suez Canal? Do we notice then? Can we pull that out?
I think as well, you could also connect emissions to radiative forcing. So you could also do what was the climate impact of the ship blocking the Nile if you wanted to go there.
Yeah, that would be interesting to do. Yeah.
We have some other questions in chat. Solomia Kachaba asks whether the resulting training data set is publicly available for your plume detection work.
If you email me, I can give it to you, but it's not currently on a website anywhere. But I'm happy to share, but it's not. Yeah.
Right. Christopher Rees asks, which SO2 data set did you use? And particularly, is this from the Copernicus Hub or the Belgian Cobra data?
Yeah, so this is what I was on about with the noisy data. So everything I've used was from the Copernicus Hub. And it was only last week I actually found out about the Cobra data, which is, from what I can see, far superior in many ways in terms of the noise of the data. So I would really like to use that for this and see how it improves my result. But yeah, at the moment, this is the stuff that's directly available from everything from the Copernicus Hub. But yeah, different retrieval algorithms would be really interesting to see the impact on this.
And Esma Tulitarabi asked a question that was in my mind as well, which is about the threshold for observing a plume. And they ask whether you can say something about the range of sources that can be detected and whether you considered validating further the attribution of the sources to particular installations or whatever.
Well, in terms of the validation, that is... So in our paper, we did the sort of example, we did a very sort of broad validation in the sense that we compared our NO2 plumes, which our anthropogenic ones, assuming they were co-located with CO2. We compared it to a CO2 data set and said, are we missing any major ones? How well do we perform? We get, well, just doing that method, I think we miss a handful of grid squares on their data set, but we do a pretty good job in terms of validating. For a more robust validation, this is a major part of the new ESA funded project that we're doing. The whole section of that is how can we go about validating? How can we make sure that what we're attributing to a particular source is correct, etc. So that is to come, I suppose.
Yeah.
And in terms of the range of sources, I mean, it's difficult. I think there is a limit to, if it's a small source, it's not going to pick up a few cars, but it will pick up major power stations. There might be ones, if a source is really diffuse, so it doesn't have a nice plume, then it might not pick it up very well. And also, as I said before, we're limited by cloud cover and latitude. So if something's really high in an extreme latitude, then it's not going to pick it up very well. But hopefully sort of time average data might be able to account for some of these.
So the titanic task you undertook of manually classifying the images, did you assess the impact of how many images you classified? Did you, if you'd only done 3,000, would it have made a significant...
Yeah, well, it started off, it was a bit of a what's the word, a rabbit hole in a way. So I started this with the help of someone at UCL called Tianran Zhang, who had done something similar, and she'd used to look at biomass burning plumes from different satellites. And she's like, oh, you need a couple of hundred images. So I got a couple of hundred, but they were just all plumes, because at that point I didn't realize actually you also need a couple of hundred of sort of non-plumes as an example of the opposite. So then I got like 400 images, and then I went through and checked them all, and actually I'd changed my mind on some. Then I needed a bit more, and then I was like, oh, how about I add another 100? And this kept scaling and scaling, and ended up with 6,000 images at the end of it. Going bad. So I did run the model each time, and the more plumes we had, the more examples, the better the model performed. It was not linear by any means, so I don't know, about 1,000 images, we were at mid-80s. And then it sort of added a bit, but yeah, we ended up with it.
Yeah, okay, thank you. Great. Well, thanks again, Doug.
Thanks very much.
Thanks for a very nice talk. I am going to bring this session to a close with grateful thanks to all our speakers for a fantastic overview.
Okay, so welcome back, everyone. We're going to pick up where we left off in the morning session, and this afternoon we have 4 speakers. So to the speakers, there's slots of 30 minutes each. If you can please leave a few minutes at the end for questions, that would be appreciated. If you do have questions from the audience, then please pop them in the chat or the Q&A boxes, and then we can put them to the speakers at the end. So our first speaker this afternoon is Martin Schultz from the Jülich Research Center, FSJ. So Martin, I'll hand over to you, please, if you could share your screen.
Okay, thank you. Let me open it again. Okay, screen sharing. Here we go. So can you see this?
Yes, thank you.
Okay, so welcome, and thanks very much for the invitation to speak today at this meeting. So the title of the talk today is Deep Learning and Open Data Systems for the Earth System Sciences. I will focus much more on the deep learning aspect. And I'd like to start as motivation with a sketch I recently let draw by DALL-E, one of the latest artificial intelligence systems. So the term I put in there is a sketch of a computer entangled in a net, and the 4 sketches that you see there are results what came out of DALL-E. So I think this is quite impressive what you can do these days to basically, even across media, basically just create new information and new knowledge. And I'll come back to that towards the end of my presentation too. But let me first begin to give you a short review of what we've done in my research group, the Earth System Data Exploration Group at the Jülich Supercomputing Center, mostly in the framework of the ERC Advanced Grant IntelliAQ, which stands for Artificial Intelligence for Air Quality. And the basic idea of this project has been to really fuse together the multitude of observational and model data that's available to interpret and analyze air quality worldwide. And so this is based largely on a a huge database that we run in Jülich for the tropospheric ozone assessment report, which has by now in the new version something like 20,000 stations around the world with air quality observations, different variables, not limited to ozone, and also some meteorological information. Then we use high resolution geospatial data to basically characterize stations with respect to things like population density, traffic, land cover, land use, and other things. We do use meteorological information from weather models or reanalyses, and well, we promise to also use satellite data, but that's actually the aspect that we haven't really covered in the project that much. And then the idea, maybe somewhat naively in the beginning, was to really feed all of that in a deep neural network and then look at three main tasks with that. So the first one is spatial temporal interpolation. So fill gaps on the map and also time gaps when there's like measurement issues or so at given stations. The second the second objective is forecasting of air quality. And the third one, if basically 1 and 2 would work, we thought that we could also apply these methods for data quality control and assessment by basically comparing the model forecasts with the measured values and then using Bayesian methods or others to get an estimate of the uncertainty or likelihood that the measurement is either okay or an error. So those are the three objectives, and I will now run you through a couple of things we've done in the project and how we worked and what we found out. And this is structured in three main elements. So the first one is this time series forecasting. So there's a series of papers that we developed in that context. The second one is spatial temporal mapping. This also includes aspects of explainable AI. There's also a couple of papers that have been submitted and published on this. And the third one is the use of video prediction methods. So here, again, maybe a somewhat naive idea at the beginning, but I think this is where great science comes from, if you dare to be naive at some point. So the idea was that if you just look at animations from air quality fields, air quality observations, it really looks like a movie, basically. And so you see patterns moving and shifting. And so why not try to use AI technologies that have been developed for movie forecasting, also very relevant for self-driving vehicles, for example, to basically try out an air quality forecast. Well, we've concentrated on weather, as I will explain later. Now, with respect to the time series work, the first study that we published in 21 was by Felix Kleinert et al. And at the time, when we sort of started to work on this, really what you could find in the machine learning literature on air quality was really very simple. So people were trying out some feed-forward networks and some other things like random forests and support vector machines, that kind of stuff, but nothing serious. So all the methods that had been developed, in particular, sort of with this or following this breakthrough publication by Krishnevsky with the ImageNet paper, had not been really picked up by air quality research at the time. We used a variant of a convolutional neural network, so-called inception block architecture. So it's basically a stack of convolutional neural layers with different filter sizes that are then merged together again. We sampled data from some 300 stations across Germany, and I think this is another add-on that was new to the literature at the time. We actually used more than 10 years of data for training, validation, and testing, and also only trained one model without any updates for the testing. The data that we used was daily statistics in order to still keep the memory and computing load reasonable at the time. So we sampled daily statistics from 3 air quality variables, NO, NO2, and ozone, and 6 meteorological variables that were actually extracted from a high resolution reanalysis. And we were at first very pleased to see that the model was able to actually capture the seasonality of the observations rather well. This had been sort of a challenge at the time. However, we also saw very clearly that the model did not preserve the width and variance of the observations. And so with each day of the forecast, we created forecasts up to 4 days into the future. You can very clearly see how the spread of the values decreases. The good thing is that it converges towards the mean value, so it approaches the climatology. It's not doing anything crazy, but nevertheless, I mean, you're just missing out on all the extreme values. Another very positive aspect of this model has been that it was very good in generalizing. So you could basically just add a new site easily without having to retrain the model or doing anything fancy, and could immediately generate forecasts for new sites. We've then taken several steps in various directions to advance this technology and improve on the results. And maybe one of the most successful ones was work by Lukas Leuven here, where he decomposed the time series into long and short-term components. Shown on the left here, actually 4 different frequencies, if you like. So baseline, then synoptic scale, intraday and journal variations. And we also moved in this context to using hourly data as inputs. However, the target was still the daily maximum 8-hour running mean concentration. In the end, it turned out that the best model for this used only 2 time components, a long-term and a short-term component. And as you can see on the plot on the right-hand side, this did lead to significant improvements, regardless of the type of model we used. So for ordinarily squares models, for CNN models, for a recursive neural network, and most of all actually for a feed-forward neural network. So that type of network benefited most from this decomposition of the time series. But you see that it improved for all of them. However, I'm not showing this here, but the problem with the extreme values persists. So we still get this very strong convergence to the mean values. This has then been solved by the next study of Lukas, who actually incorporated then the meteorological forecasts. So the idea up to then had been to only use data up to present and basically attempt a full forecast, including forecast implicitly for both the weather and the air quality. We've then considered basically how would we design a possible operational system for air quality forecasting, and figured that we could rely on meteorological forecasts for such a system, but we would basically replace what is currently done with the chemistry transport model through our machine learning approach. So in this latest study, we used data from all over Central Europe. So basically Germany, including plus Netherlands, Belgium, some other areas around. We still maintain the split of the long-term and short-term data, but then we have 2 extra branches, one for the meteorology, which includes the future, and the other branch for the air quality variables. So all in all, we again train on some 300 stations, which all in total leads to about 800,000 samples. Also for the first time, at least that's the first study I'm aware of, if you know of others, please let me know. We are actually doing a comparison to an operational CTM-driven forecasting system from the Copernicus Atmosphere Monitoring Service. This is the ensemble median that's displayed on the lower left in the orange line. And you can see that our machine learning model is actually doing much better than this ensemble average from CAMS. And this is both with respect to the mean squared error, but also the mean absolute error, as you can see on the right-hand plot. So as a result, we could say that in this line of work, we've achieved a very meaningful forecast over 4 days. It's sufficient to have a meteorological forecast over the same time range. We can also beat the regional CTM ensemble, and as I'm showing you here, we now actually are much better in capturing the extreme values. We are still not getting the real extremes, so the almost outlier values, if you like, but at least in terms of up to the 95 or so percentiles, we're doing a pretty good job now on capturing the distribution. The second line of research that we pursued is this mapping approach, where the general idea has first been, in our first study by Clara Betancourt, to just explore how far can we get with all these geospatial information that we have in our database. so all these variables like population density and so on, to make a forecast or an estimate of average ozone concentrations. And so you see here a snapshot of the list of input data. So these are things from land cover, for example, permanent wetlands in 25-kilometer around a measurement site, croplands, urban and built up, and so on. You also see other variables like wheat production, rice production, or NOx emissions, NO2 columns from satellite observations, or population density. And then all of these have been fed into 3 different types of networks: a linear regression algorithm, feed-forward neural network, and a random forest. One can see that the random forest is doing best here in almost all of the metrics that have been looked at. So we've, as target values, we used 5-year averages of either average values, daytime averages, nighttime averages, median, and so on, as you can see on the left column of this right-hand side table. The results are maybe not exuberant, but at least they're reasonable. So we do get a clear signal that yes, there is information in these geophysical variables informing us about the expected ozone values. We've then taken a next step, the second paper by Clara, where we then try to extrapolate basically these values onto the global map. But in order to remain meaningful with the extrapolation, we applied several XAI techniques, in particular cross-validation and a technique called the area of applicability, where you basically look in the feature space how the trained observations cluster, and then you basically group all the other observations into this feature space, and if the distance exceeds a certain threshold, you'll basically discard these as being too uncertain to make a meaningful prediction. You can see here on the map, the light blue shaded areas are the ones where we have pretty good confidence that the model is giving a reasonable prediction. Specifically, this means in the range of ±4 ppb. The darker blue areas are somewhat more uncertain, but still meaningful, whereas in the gray areas of this world map, we basically don't have any meaningful information to fill in the ozone, the gaps from the observation network. And that's then the result with respect to ozone. So if you look more carefully, I'm not showing this here, but we've done some more careful cross validation against the stations in these regions where we have the white rectangles. And this shows actually a pretty promising results that in principle, this technique is working. Now, of course, this is a rather static extrapolation and really more like to get your fingers wet. And then, of course, the next big step forward would be to include the temporary variability, meaning basically all the variability that's introduced by the weather conditions. We've done some work here with using basically techniques for data imputation, in particular graph machine learning for the so-called correct and smooth method, together with the random forest to fill in the data gaps for a year of data, again, observations from Germany. But there's still a lot more that can be done and that we are planning to do. And this leads me to the third branch of research that we've been doing with the radio prediction. So here we've focused actually more on weather predictions, simply because we had the weather data available as field data, and also simply due to the funding situation that there were other projects, particularly the Maelstrom project funded by the EU, that we could use to explore these methods further. And here we've exploited some more modern machine learning techniques. In particular, at the time when we started this work, there was this SAVP method coming out. This stands for Stochastic Adversarial Video Prediction. And this is a combination of a generative network, a so-called GAN, and a variational autoencoder. The idea here is that a generative network can create distributions of the variables that are closely matching the actual observed distribution. So you're not getting this convergence problem towards the mean. However, what people often find when they use these generative networks is the so-called mode collapse. So there are too few states basically coming out of the model. And this is then counteracted by this variational autoencoder. As a competitor model, we use a so-called convolutional LSTM, so a CNN, convolution neural network, combined with a long short-term memory network to capture the temporal aspects. And there are some results shown here where we do a 2-meter temperature forecast for 6 and 12 hours. You can see in particular on the error plots on the right-hand side that both models still show pretty large errors, in particular in the mountainous regions, the alpine region. However, in principle, you do get, again, some skillful forecasts, not only with respect to MSE, but also with respect to the anomaly correlation coefficient and some other metrics that we evaluated. This line of video method application has been extended now in the Maelstrom project to tackle downscaling. Again, we're first focusing on weather data here, not atmospheric chemistry data. So the idea here is to basically learn 2 tasks at the same time. So a classic machine learning task of downscaling, they actually call it super resolution, is indeed really just to generate credible or good-looking super resolution images, whereas in the meteorological application, and then of course also for air quality, you would need to also learn a bias correction, because if you, for example, run a chemistry transport model in, say, 1 kilometer resolution, you will definitely generate different distributions compared to running this kind of model in, say, 30 kilometer resolution. The network approach that we applied here so far has been a UNet architecture. These have become quite fashionable in the weather AI science. And this is a factor 8 downscaling that's shown here on the plots. Now, the new thing that we're tackling, and this brings me back to the title page with the DAL-E model, is to actually start using atmospheric representation learning. And so we've engaged in a project launched by Christian Lessig from the University of Magdeburg, which is called Atmospheric Representation Learning. The idea is to really fully exploit the richness of information from the ECMWF Era 5 reanalysis, so several petabytes of data, train one huge machine learning model, actually transformer architecture, and then use this model for several downstream tasks. And among those would be downscaling, classification, for example, hurricanes, predictions, missing data imputation, and then of course also air quality applications. There's also a hope that we could use this kind of model then to even gain new scientific insight from machine learning, which is actually one of the main challenges that's still out there. That so far, in particular the weather community thinks that machine learning might well play a huge role in replacing certain parts of operational systems. But so far, there's no clear path to how we could use machine learning to actually gain new scientific insight. To explain this a little more, how this representation learning works, let me give an analogy here from GPT-3, so one of these huge natural language models. And the main point is that you have really one model that can then work on many tasks. And what's shown here is, for example, how this GPT-3 model can actually do arithmetic. So note that it has been never trained to calculate. It has only parsed texts from the internet, millions of texts, of course, even billions. But then without any training, just basically giving it one example, that's a so-called one-shot inference, you can actually start adding or subtracting numbers. So there's some examples shown here on the left-hand side. So you type in a question, what is 48 plus 76? And the answer is 124, correct. On the right, lower right, you can see in this plot that this type of inference across domains basically requires really huge models. So as long as you're below something like 10 or so billion parameters, trainable parameters, the performance for this task is really poor, and it really only significantly ramps up once you reach this threshold of model size, and associated with that also data size. And these kind of scaling laws seem to apply for many different tasks in the, let's say, cutting edge AI. And this is what we would really like to exploit in the atmospheric representation learning as well. So the architecture that we want to employ is a transformer architecture. In principle, it's different layers that have so-called self-attention and cross-attention. So self-attention within a layer, within a variable, and cross-attention across variables. I'm not going to show you too many details here. There's a so-called embedding network coupled before this actual transformer to learn an encoding basically from these spatial fields. So these are small snippets of on the order of 9x9 grid boxes, basically that are then encoded into so-called tokens, and these tokens are what are fed into the transformer network. And this actually works. So here's some results showing you how basically a forecast looks versus the comparison. Note that these are only 1 hour forecasts, so it's difficult to see from these 2D plots how well this works, but the 1D line plot on top, which is actually just sampling the grid boxes line by line, shows you that indeed there's no distinction between the prediction and the reference. We've also tested this as the so-called zero-shot performance, where you can see basically the in-training on the lower left is the best, of course, in terms of quality. Persistence on the right is our reference, our baseline. And you can see that both zero-shot task, one of them is the random masking of arbitrary pieces of these grid boxes. That works pretty well. And also a real forecasting task where you mask basically systematically the future values also still performs much better than the persistence. And this is without any further adaptation to the network to do the real forecasting task. And then, of course, since this is a presentation about air quality, this kind of network will offer us tremendous opportunities to do the kind of tasks that we've set out to do in IntelliAQ, like spatial temporal mapping, air quality field forecasting, and also air quality downscaling to finer resolutions. Let me say that we're not alone. So there's a recent paper called Pangu Weather, which is also following a similar concept. There are several differences to the concept that we have. This is just a snapshot of their model architecture. I'll skip over that in the interest of time. They're showing spectacular results in their paper, even outperforming, beating the operational IFS model with several variables. And on the right-hand track, you find a hurricane track that was severely mispredicted by ECMWF, but where their machine learning model is a much better forecast. Now, one has to question whether these results are really that spectacular. The good points of the paper are that indeed they're using not only the MSE. This has been a flaw in several, in particular, older machine learning papers in the weather and also air quality domain, that the only evaluation metric has been a mean square error. And this is definitely not meaningful for evaluating atmospheric fields. They're also evaluating several fields and tasks, so it's not just a snapshot of only one variable or so. However, they might still be cherry picking, in particular with respect to the hurricane track analysis. And if you look closely at the plots that they produce, there are some apparent artifacts and smoothing of features that are not at all discussed in the paper. So this brings me to call out for some remaining issues. So in particular, we still don't have standard benchmarks for weather forecasting by large-scale models, let alone for air quality forecasting, which makes it very difficult to judge and compare the results from different studies. We don't have standardized evaluation metrics, so what exactly are good target metrics so that we could really say, okay, this is better than a CTM or better than a weather forecast model or whatever. And also, we don't really have one clear baseline model that could act as a competition or a competitor model, basically. Also, we find that still all machine learning models underestimate extreme values. I've shown you that in Luca's study, we're getting pretty close to at least the 95 percentiles or so, but we're still missing the real extremes. And in part, this is related to the L2 loss that's still used very widely in pretty much all atmospheric machine learning studies I've seen. There are some variants, in particular, if you look at generative models, of course, but even then, often there's still at least some L2 loss sneaking in. There are some other challenges, like how can we actually train these really large models with more than 1 billion parameters? I mean, this is even a challenge for large companies like Google and so on. They can only afford a certain number of training runs for these beasts. The other big question, and I think this is actually a very interesting philosophical question that I'm very happy to discuss further. Do we actually need physical constraints in the model? So I think there's now 2 schools of thoughts developing. One claiming that there's an absolute necessity. Without physical constraints, there's no way forward. We will never reach a truly skillful forecast. However, the other school of thoughts would actually say that, well, if the model is large enough, similar to what I showed you with GPT-3 and the arithmetic, maybe there's a way to that the model learns the physics of the atmosphere by itself, and we don't have to teach it these laws. And finally, how can we consistently leverage the enormous richness of observational data? I was asked to say, don't say data assimilation, because there's a very strong opinion, in particular in the weather community, what data assimilation is. But in some way, I think if we train machine learning models to make use of the huge deluge of satellite data and other information, this is nothing else than a new way of doing data assimilation. Just to come back to this first challenge, the benchmark data sets. So there's a recent publication by Peter Düben and co-authors. I was glad to be involved in this work to actually define challenges and benchmark data sets for machine learning in atmospheric sciences. I'm not going to go to too many details of this paper, but I'd like to flesh out this main table, which defines requirements that should be present in any benchmark study or benchmark paper. And we group those into 2 categories, order 1 and 2 requirements. The first group, absolutely essential. So if you don't follow those requirements, well, you shouldn't consider your work a benchmark. And highly recommended requirements in the second category. And these are requirements like data should be available online without access restrictions, so that indeed people can grab the data and work on it. There has to be a clear problem statement for meaningful tasks in atmospheric science. The data input has to go into a high-level open data science language. So that basically you need to provide a reader routine for coupling these data to the machine learning workflow. And very clearly define evaluation metrics, both analytically in the code and the paper, but also with code examples, how to actually evaluate that. Furthermore, there should be some simple example machine learning solution provided, both in the paper and the code. You should provide code for visualization and diagnostics, tests for physical consistency and explainability, and finally, some benchmark for the computational performance. With that, I'm reaching the end of my presentation, and instead of putting up concluding remarks, I'd like to extend an invitation to a workshop that we are organizing in Cologne next spring. And I'm actually very grateful to Paul Griffiths to agree to be a co-convener of this workshop. This will be a dedicated workshop on machine learning for air quality. The rationale is that we've seen several activities mushrooming up for machine learning in the weather domain, but so far there hasn't been too much of a consistent effort to really provide a platform and a forum to discuss what needs to be done in terms of machine learning for air quality research. And so this is an opportunity. If you're interested, you can go to the webpage listed above and register and in fact, and yourself basically to attend the conference. And with that, I'm done, and thank you for your attention and look forward for a question or 2.
Well, thank you very much, Martin. That's really interesting talk. So maybe I'll kick things off with the questions. It was really interesting to see how well your machine learning forecast was doing with respect to the CAMS ensemble. I didn't catch the date of that publication, but I just wondered how far along that comparison is, so comparing the ML forecast to the CTMs, and whether or not you looked at the individual CTMs of the CAMS system. Some of those models might do better than others.
Yeah, no, we haven't done that yet. So the publication has just been submitted AI for ES. Actually, it's the last publication of Lucas for his PhD thesis, and he's now currently trying to write it up. We clearly have a lot more planned for this model. So in fact, I've submitted a proposal to operationalize that. We've gotten in contact with the South Korean environmental agency, and they would be very keen on putting this into operation. And if that flies in that context, we will definitely do a lot more of validation work and check the basic conditions under which the model performs good or bad.
Sure. Okay, thank you. So we've got a question in the chat from Matt Amos. Matt asks, what's the benefit of having a massive model that solves multiple problems rather than having individual models that solve specific tasks? And Matt's understanding was that outside of neural processes and NLP models, most machine learning models are best at specific tasks.
I would challenge that opinion, and the reason is that indeed, as we see from this natural language processing, and also the cross-medial, let's say, work that has been done recently, like the DALL-E system, which basically crosses over from language to images, that it really creates a new dimension, basically, to have these huge representation models with representation learning. Because you can capture a lot more of the complexity of the phenomena, and there's so many, like for example, if you just draw a spectrogram of atmospheric variables like vorticity or so, you find that there's a signal in pretty much all scales, and to capture these scales in one model, you really need a huge monster. The other aspect of that is actually the at least potential gain in efficiency, in that you need to train this beast only once, and then with very little additional computational effort, you can base all these different applications on it. So it's a bit maybe comparable to the situation. I mean, if you would like to use a weather forecast model, you would also not want to use a dedicated weather forecast model that you run yourself then for your CTM. But instead rather use the best weather forecast model that's out there, that's been developed independently, with taking into account a lot more complexity and scales and features.
Okay, great, thanks, Martin. I think that's everything in the chat. So thanks very much, Martin. Thanks for that very interesting talk, and I'll introduce the next speaker.
Okay, yeah, thank you very much. I'll listen in for a little longer, but then I'll have to go back to my other meeting here. Yeah. Thanks very much.
You're welcome. Okay, so our next speaker is Makoto Kelp from Harvard University. Thank you for joining us. I know it's quite early where you are in the States. And so over to you. Thank you.
Great. Let me share my screen. Does everything look good?
Yes.
Okay. Well, thank you, Ryan and Paul, so much for the invitation. I'm happy to present some of my work. And I want to start by saying that global modeling of comprehensive atmospheric chemistry is getting more and more computationally expensive. And it's not simply because we're trying to get finer spatial temporal resolution in our complex 3D models. It's because we keep wanting to add additional scientific sort of knowledge into these models. And right now, our ability to the scientific advancements we make are outpacing our ability to model it. This is just a figure showing on the y-axis horizontal resolution of a series of climate and GCM models. And on the x-axis is the years, and you kind of see the higher complexity of these models, such as coupled to atmosphere ocean models, Earth system models. We're really starting to level off these sort of performances in relation to Moore's law, simply because we're really adding so much information into these models. And foremost, the largest cost in running these models really comes from the atmospheric chemical mechanism. On the left, I'm showing you results from Seb Eastom's GeoSchem high performance paper, where on the x-axis, we have the number of cores or computer resources we devote to a simulation. And on the y, it's the time that it takes for each component of the model to run. And although chemistry scales perfectly with the resources we give it, it still dominates the cost of this simulation. So nearly half the time of a CTM model run is spent on the chemical mechanism. This is because chemistry requires the solutions to couple differential equations, in that these relationships are very stiff. You have lifetimes that range from the order of seconds to many, many years in the atmosphere. And it's also very high dimensional. And, GeoSChem, the model that is we run in our group, it has over 200 species. And this is in stark contrast to weather and climate models, which do have complicated relationships, but the dimensionality is much lower. And really the bottom line is that adding this comprehensive chemistry into Earth system models or coupled climate models is really computationally infeasible right now. It slows something that already takes weeks into months. And so early on, through work in multiple papers that I've done, we've identified machine learning as a potential solution to this problem, neural networks specifically, for 3 reasons I list here, where neural nets are non-parametric universal function approximators, meaning that they can map any input to output regardless of nonlinearity or complexity, which we know that atmospheric chemistry relationships, it's sort of very prevalent in this field. 2, learn to predict based on large data sets of repeated patterns. If anyone's run a global 3-dimensional model, GeoSChem, WRF-Chem, any of these models, we can generate a lot of data really easily. And 3, and most importantly for neural networks, it's proven to speed up the solution to these ODEs at orders of magnitude speed up. This is because you're essentially replacing that expensive higher order solver with a series of matrix multiplications where these values and weights of these matrices are learned through a training process. However, I'm going to talk a bit about physical constraints in the next few slides. This is work that I did before starting grad school. On the left is a study I did where we tried to emulate a chemical mechanism in just a simple box model, CBMZ box model, just with 77 gas phase species. We trained it just using T to T+1 time pairs, or just a single chemical time step. We curate that data set, mix it up, and then train the model on that data. Now we have this learned chemical integrator. It's really great for the first few time steps. When we trained this, we had very high R-squareds. But when we run it forward in time in a classic Euler integration fashion, in which the outputs are the inputs into the next time step, we accrue error very, very quickly. And we have this runaway error growth. And by the end of a 1-day simulation, it's basically useless. The error is way too high. Similarly, Christoph Keller and Matt Evans at a similar time created a random forest chemical solver integrator, put that in GeoSChem. So it's a different machine learning algorithm, a different chemical model, and still witnessed this large error growth. And, they found that the random forest is actually slower than the actual Fortran chemical mechanism solver, but whereas the neural network is much faster. So we thought, okay, we need to use a neural net just for this speed up sake, but we're encountering this error growth problem. And I want to list some reasons why we should use machine learning and why we shouldn't in the context of a learned chemical solver. Why we should use it is that chemical calculations are very expensive. It's currently the bottleneck in a lot of these climate, comprehensive chemistry, atmosphere models. It's highly repetitive. So, if we simulate the 3D grid, there's so much redundancy in this grid, from the remote ocean to higher up in the atmosphere. One grid cell to the next look very similar to each other. And so there's no reason to invoke a full chemical solver for somewhere over the oceans when the chemistry is much simpler. And 3, it's fully deterministic, meaning, there's no stochastic parameterizations involved, makes the learning process a bit simpler. Why we shouldn't, it's very high dimensional. Most successful neural network studies are not super high dimensional, might have 10 or so inputs to predict a single or 2 outputs. Whereas for chemistry, we have hundreds of evolving inputs and outputs. And really, we're seeing that there's a lack of physics-based constraints, which potentially lead to error growth, and the previous speaker talked about this a bit. And I'm also kind of on the fence if this is needed, but it's the idea that, just training naively on the time pairs of over a single chemical time step will really not help this error growth problem. And so my first project in grad school was, let's try to fix this error growth in a box model setting. And I created this framework here. And I think the ideas are pretty interesting for, working with large data sets and chemical mechanisms, where we created this new framework that compresses the dimensionality into a lower dimensional subset. And it also has this built-in temporal constraint so that during training, we predict a trajectory so that the model learns sort of multiple time steps into the future while still remaining a single step integrator. And I'll describe what that means here. So we used a slightly larger box model. This is CBMZ with the mosaic aerosols. So it's 100 species with 4 meteorological forcers. Temperature, pressure, relative humidity, and the solar zenith angle. What I do is just at time step 0, I have 101 concentrations, run it through an encoder and out a decoder that compresses the dimensionality into these features that are there are much fewer. I think we compressed this from 101 species down into 16 without loss of accuracy. And then we run it through a operator, we call it. This is just a neural network that pushes the time step forward 1 time step into the future. What we do is then feed back this loop during training. So it's predicting multiple time steps with these exogenous weather environmental variable forcers. Then we have 24 hours of predictions, run that through the decoder, back out into the original high dimensional space. And what we see is that this kind of applies physics-based constraints to really help learn over a time horizon. So what I'm showing you here is the top panel is just the sample trajectories with the error associated with it, where the first row is just that naive t to t plus 1 time pairs. We see that we run it forward in time, it explodes. That's really common with these neural nets when we kind of just learn over a short time period. It doesn't extrapolate very well, error accumulates. Whereas this current model framework, we're able to get sort of a error growth. There is no error growth over a 24-hour time horizon, and we train it for 24 hours and it works past almost to 5 days. So it's learning the diurnal cycle. It has greater information, but it still is a single step integrator. Okay, and most importantly, we see that we have these speedups still. So over to simulate the time to simulate 1 million grid cells for the CBMZ mosaic box model in Fortran, it takes around 5 hours. Doing this on a single CPU with this neural network neural network model, which takes around a minute. So it's a 260 time speedup. So it's this orders of magnitude speedup, and you could get additional speedups using sort of more computational resources. Okay. So that's all well and good, but a lesson we learn is that box model land, which is really great to refine our machine learning methods, doesn't necessarily scale to a more complex CTM. And so in order to test out these methods and ideas, instead of using the full GeoSChem standard mechanism, which has over 200 species, we use a simplified it's called the superfast chemical mechanism. It only has 12 species, and it's just generally representative of tropospheric ozone at a synoptic scale. And you can see the comparison of the superfast implemented in GeoSChem versus the standard GeoSChem. Ozone is, from the eye test, it's fairly similar. It looks fairly realistic. The NOx in superfast is much higher because there really isn't any NOx not many NOx loss pathways. It doesn't have nighttime chemistry, so it's very simplified, but for ozone, it looks okay, and this is a great way to test our methods. So I benchmark this in GeoSChem version 12 at the coarsest resolution we have, 4x5. And over a 1 hour chemical time step, which is the time step we look at, we track 20 variables for this neural net. We have 2 physical variables, temperature, air density, 6 photolysis frequencies that governs the change of concentrations based on sunlight. and 12 gas phase species, so the concentration of the species. And as you can see, for a 1-month data set, we would have roughly 62 million samples. So this is not really a data poor situation at all. We have enough data to fully kind of explore the parameter space. And I trained this I do all my training in the year 2016 and then tested 2017 the following year to avoid any sort of autocorrelation effects. And so what that looks like in a sort of GeoSchem chemical transport model context is I basically rip out the chemical module and replace it with this machine learned integrator. So, this looks very similar to what I just showed you for my box model neural network emulator, but this here is just the same thing where we input the 12 chemical species and we have these external variable forcers that are fed in during the prediction of advancing the time step. And so, this is written in Python and GeoSchem is written in Fortran. Just coupling this together was a nightmare on its own. But, once we're able to have Fortran and Python to talk to each other, we can do a lot of different kind of things. And first, I explored offline training, which most machine learning kind of studies involve offline training in which you generate a large archive data set and then curate that data set, train your model on that data, and then you have your learned model. Whereas online training or sequential training is each time step in GeoSchem itself is treated as a new machine learning training session or epoch. And so what that does is during each chemical time step, as I run GeoSchem itself, it trains the machine learning algorithm in tandem. And I'm going to show you what these different methods look like. And so these are trained on June, July, August 2016 and tested on July of 2017. This is all looking at surface ozone and their error metrics. So first row, this is just that naive T to T+1 single chemical time step pairs. We see that when we do that, shuffle it up offline, implement it into GeoSchem, immediately super high error. It basically predicts a very high ozone value just for every single time step. It makes the same prediction. So it really didn't learn any of the sort of dynamics at all. Then I do this offline 24-hour recursive. So just kind of like what I did in that box model paper where I can archive the photolysis frequencies and these environmental variables and do offline training, just project the trajectory during training. And that, dampens error by over 10 ppb for ozone. And you can kind of see by the wiggles that it kind of learned a bit of the diurnal dynamics. However, 20 ppb is still way too huge an error for a chemical solver for ozone. What I then do is say, okay, this model is better than the top row model here. It learned the relationships a bit better. So let's take that model, put it in GeoSchem, and retrain it online in GeoSchem as it runs. What that does then is we dampen that error down to 6 ppb, and we see kind of a hemispheric bias here, where the south is a little low, the north is a little high, but the error is dampened by quite a bit. We attribute this kind of gain in accuracy due to each chemical time step is the full realization of the 3D grid. It's representative. We're not over or under sampling any remote or urban environments. And we think it's sort of a reformulation of the training sample that helps this. But finally, I thought, okay, why should I train something offline, retrain it online? That's very expensive, time consuming. Why not just train this online from scratch to begin with? And we see that that does the best by far, 1 ppb of error and not much of a spatial bias here, very low bias. And this is because basically, if you train something offline and retrain it, it's hard to unlearn some of the representations in this model. So I thought, okay, let's go use this online learned framework from scratch, and let's do this for a whole year in GeoSchem. This hasn't been done. All the Keller and Evans paper was just for 1 month. Let's see how this responds over a whole year. And we find that the model is stable and error does not explode or accumulate over the course of a year. And so one thing I learned, though, is that neural networks are very good for very narrow tasks. Sort of what the question posed in the chat was. That's sort of my experience, where a neural network predicting all species in a mechanism is less accurate than one that is predicting for a single species. Similarly, a neural network trained for the entire year is less accurate than one trained for a specific season. And so with this, I created these sets of seasonal solvers for each chemical species in this mechanism. And in the top left corner of these graphs is the sort of mean normalized bias for the entire year, and they're all within plus or minus 10%, which is great. This last graph, the bottom right, it's a little misleading, where HNO3 is actually a kind of a dummy species in this mechanism. There's no chemical loss, so it just accumulates error. Probably shouldn't have included it to begin with, but oh well. There's isoprene here. That's quite large of an error, but we actually get the hotspots of isoprene correct. And a lot of this is due to small concentrations in sort of remote grid cells that is more just kind of numerical noise. But how we read this is for the normalized mean bias here. We have different seasonal fits of accuracy, where in January, February, let's look at NOx in red in the top left panel, we have some negative bias. We go and then switch to March, April, May, to a new set of solvers. We have a positive bias, go through that season, shift to a June, July, August solver, and you see this huge error perturbation down to almost negative 30, normalized mean bias. But then over the course of that season, that error starts to go back up to that zero baseline. And we hypothesize that in some way it's learned its own sort of Le Chatelier's principle, where it tries to undo the error that might have accumulated in the previous season. These solvers have different implicit biases, and in a way it's trying to reverse and correct that error. So really we're seeing that different sets of solvers can act as its own form of regularization. And you can kind of see that relationship in other species too, where CO in black here builds up and then it is sort of depressed back down in the next season. But overall, this doesn't explode and error does not accumulate over the course of a year. Okay, I want to be cognizant of my time here. This, I'll just go quickly through this. Basically, ozone dynamics are very well captured in both polluted urban grids, where we have NOx concentrations that are released in a very regular emission process in Beijing, and in a more remote ocean-based grid cell where NOx is very low, we can also capture that ozone. So we are able to do that at a synoptic scale. And this is going to be my last content slide. And really, what the problem is right now is that we're not able to capture correctly the concentration distributions at the tail ends of this distribution. So what I show you here is ozone. If you look at the machine learning solver versus the reference case in GeoSchem, by the eye test, it does pretty well. Fractional errors can be up to 20%, but basically it's within 10 ppb. It's realistic, and that's usually a cutoff for just even normal chemical mechanisms. If we look at NOx, though, this is where the problem lies, where we're able to capture the hotspots of NOx correctly. So that's good. But when you look at the fractional errors, it can get up to 200% error in the remote latitudes and in the upper troposphere. And this is a problem because even just like a PPT level of NOx, so very, very tiny concentration, can have a massive effect on the chemistry of the atmosphere, can change ozone, and really drives the dynamics of the atmospheric system. And what I'm finding is that neural networks are really great at capturing the bulk of the distribution of, the concentration distribution, but getting the very small concentrations, these aren't going to really move the needle during training, and you can underestimate the high concentrations, and these tail ends really limit the sort of practical application of machine learning within a CTM, because it requires such a high specificity when we're sort of dealing with the chemical solver as the ground truth. I'd like to say that the speed up we find is fivefold, so 5 times faster than the GeoSChem solver. But again, this accuracy is really what's limiting it. With that, thank you for your attention.
Well, thanks very much for that really interesting talk, Makoto. Excellent. Maybe I'll kick things off question-wise while others come in. Well, I agree with you that there's certainly a need for this type of work, and once it's up and running, it'll have massive benefit. We'll always find more reactions and more chemical species to add to models. I don't think we've reached peak number of species in models for sure yet. But it does strike me that the barrier to get something like this in a model and up and running is probably quite high. There's people who run models, a subset of them look under the hood and edit the code, and then probably only a subset of them are proficient in machine learning to do this sort of thing. I mean, would you agree?
Yeah, so, there's some things I think machine learning is great for. I don't think, replacing full components of a parent complex model is the best. I mean, in terms of a chemical mechanism perspective, I think it's great for compression, using this encoder decoder framework. I think that has promise, and I think, but, if we use the ground truth of emulating a high order implicit solver, I don't think we're ever going to really get there using a statistics-based method unless you do, invoke much more computational tricks than what I have done so far.
Right. Could you perhaps comment as well further on, you outlined the possible frustration of most models being written in Fortran, whereas I think your ML code originated in Python? Yeah,
I mean, I think if I were to do this right, knowing that it would work, I would probably write the neural net code in Fortran, just write it once, and that's the static model. But because I didn't know what the architecture would look like, and Python just has all the easiest to use machine learning libraries, what I did was develop just like a C interface. So basically the CFFI, if you've heard of that, it's like a C bridge that connects calls Python from Fortran via a C connector. But really there isn't much out there. I found that, there are packages that you can do neural net stuff with Fortran, but it's very simple. I wouldn't be able to do an encoder decoder, and I couldn't even predict multiple outputs. So I had to just write this on my own.
Right. Okay. Any other questions here? Let me just look in the chat. No, I don't think so. So in which case, thank you very much again. And we'll move on with the agenda.
Great. Thanks so much for the invitation.
You're welcome. Okay, so our next speaker is Angarad Stel from Bristol University. So over to you. Thank you.
Hello. I will just get my slides up, hopefully. Oh. Right, hope that now works for you guys.
Yes, we can see the slides. Thank you.
Great, thanks. Oh dear. Sorry, new computer doesn't quite work how I expect it to. Right, hi, I'm Angarad Stel. Yeah, I was doing a postdoc at Bristol University, and that's also where I did my PhD, although I've now left to work as a data scientist. But today I'm just going to be talking about some of my work that I did during my PhD at Bristol University, where I looked at approximating atmospheric models in order to learn more about the global methane budget. This has now been published in ACP, if anyone wants to take a look in more detail. So just to start us off, this is probably familiar to quite a few of you already, but this is the graph of global methane mole fraction that's taken from NOAA. And this is just showing the mole fraction of methane through time. And as you can see, as we go through time, the growth rate has changed quite a lot. And in particular, a large amount of attention has been paid to the plateau in the methane growth rate between 2000 and 2007, before the mole fraction began to rise again. Alongside these measurements of the mole fraction, there are also measurements of the carbon-13 to carbon-12 ratio in atmospheric methane, which should help us to figure out the cause of these changes in the methane growth rate, as these different sources of methane emit methane with different carbon-13 to carbon-12 ratios, and different sinks remove different amounts of methane with carbon-13 and carbon-12. So loads of different studies have tried to look at this, and using the same set of observations, but different global models and different inversion systems. And they have kind of produced a large range of almost contradictory solutions to what's going on with the methane growth rate. So things like the wetland emissions, ruminant emissions, fossil fuel emissions, biomass burning emissions, and also the hydroxyl radical and methane sink have all been implicated. So there's clearly still work to be done here on ensuring that we can do accurate global modelling studies with adequate uncertainty quantification. And in this talk, I'm going to go through some of our work on these global modelling studies and show a sensitivity analysis for the global methane budget which has helped us to identify some of the gaps in our knowledge. So typically when we do methane modelling studies, we have to take a set of methane sources and sinks and put these into an atmospheric model alongside a delta value. This mole fraction delta value can then be used for lots of different types of analysis. So for example, pairing two observations if you want to optimize our sources and sinks, or carrying out a sensitivity analysis, which can show us which sources and sinks have the biggest impact on the mole fraction and delta value. But a lot of these types of analysis can require millions of simulations, which can take a very long time. So one way people have made this feasible is to use a really simple model, such as a two-dimensional box model shown here. So this is just a really straightforward example where you've got emissions and losses in a northern hemisphere and a southern hemisphere, transport between those hemispheres. And this type of model will run really quickly, but has very limited spatial resolution in your inputs and your outputs, and doesn't have a lot of other features such as interannual variation in transport. So one of the alternatives is to then use a much more complicated three-dimensional chemical transport model, such as MOTES. So here's some of the output and input shown here. But these models take much longer to run, and obviously that's really problematic if we do require millions of simulations. So previous work has tried to overcome this using either like a linear approximation of the model or an adjoint model, which both have their own set of disadvantages. So for example, like the methane budget is not linear, and also an adjoint model can be really difficult to set up if it doesn't already exist for your model. So in our work, we've done something a bit different, where we produced millions of 3D chemical transport model simulations, but without assuming linearity. And this is also readily applicable to any model. The method we used is a Gaussian process, which is a type of machine learning. So I'm just going to talk you through a very simple one-dimensional example here, where all you need is a set of model inputs, and you then run your model for this set of parameters in order to create a training data set, which are these blue points on this plot here. And then all the Gaussian process does is kind of effectively interpolate between these points between the known points in the training data set, but without assuming the form of the function that maps the inputs to the outputs. Then the Gaussian process can predict the value of the model output at any input value. And this prediction is shown as the black line on this plot here. The Gaussian process also produces an estimate of how uncertain its prediction is, which is shown by the grey shading here. So that goes to 0 at the training data, and as we go further away from the training data, it gets much larger. But that's a very useful feature for scientific prediction. So just as then a quick example, if you have an input value of 8 on this plot, so this orange point here, the Gaussian process is going to predict an output value of 1, but the uncertainty here is really large, shown by the orange line. This is because the this point isn't being bounded by training data. And of course, this uncertainty is really quite large, and we don't really want this kind of uncertainty in our study. So we've excluded examples like this by making sure that we don't predict outside the range of the training data. And also, you have to space our training data well to make sure there aren't regions where we don't have training data nearby. So the real benefit of this is that instead of taking hours to run a 3D chemical transport model, this took 40 milliseconds. So we can get the same, well, predicted output much, much quicker, and then be able to generate many more simulations and do more complicated analyses. Yeah, so that was our nice, simple example of the Gaussian process. Of course, our paper is more complicated and actually has 28 parameters, which describe the sources and sinks of methane, which is shown in this table, along with the ranges examined in the Gaussian process. As well as having 28 parameters, the output that we are trying to emulate is actually a time series from 2000 to 2012. So again, our case is a bit more challenging than what we saw on the previous slide, but the same principles. So in order to make sure that we could sample all these different parameters, we did hold some of the more minor terms in the methane budget constant. So these were not included in the 28 parameters. We called these the invariant parameters, which are shown with the kind of dark green boxes around them. So we do look at the uncertainty from these parameters later on, but they are not included within the 28 parameters that are varied within the Gaussian process. So of those 28 parameters, they describe the magnitudes and delta values of the sources. So we've got wetlands, freshwater, agriculture, rice, waste, fossil fuel, biomass burning, geological sources. There's also a set of parameters that describe the losses, the magnitude of the losses, so hydroxyl radicals, stratospheric losses, chlorine, soil. And then another set of parameters that describe the spin up. So got the amount of emissions during the spin up, as well as the difference between the source and the loss in the spin up. There are also 5 parameters that allow the trend of the 5 largest terms to be changed by a linear trend. And these parameter ranges are actually quite large, designed to be inclusive of like the majority of possible values and derived from literature. So it's this very large range of 28 parameters that we need to sample over in order to get model outputs for, in order to create our training data set for the Gaussian process. So as we saw previously, we want to make sure that our training data is evenly spaced to avoid large uncertainties in our predictions. So we sampled our parameter space using a Latin hypercube design. So here's just a very simple 2-dimensional example of this, where parameter space in this case is divided into 4 columns and 4 rows if 4 samples are to be taken, and then 1 sample is taken in each column and each row. And using this Latin hypercube design, but instead in 28 dimensions, we took 270 input parameter samples in order to train the Gaussian process, as well as an independent Latin hypercube design of 90 input parameter samples in order to test the Gaussian process. And we also used another Latin hypercube to sample just the 9 invariant parameters, just to have a look at the effect of changing those on the output. And then we take all of these sets of parameter inputs, we run them through our model in order to generate our generate our sets of output values for each set of inputs. And then these model outputs combined up to a hemispheric value for the mole fraction and the delta value. And each of these 4 hemispheric outputs will be emulated by an independent Gaussian process, although it should be quite trivial to extend this to emulating grid cells of the model if we decide that. But before we go ahead and train the Gaussian process, we'll just take a quick look at the model output we are trying to emulate. So here, these are just the 4 outputs I was saying. So southern hemisphere mole fraction in the top left, northern hemisphere mole fraction in the top right, southern hemisphere delta value bottom left, and northern hemisphere delta value in the bottom right. And each of these orange lines is one of the 270 model training simulations that we had, with the blue being the mean of those. And the black points are the observations that we've just put up here for comparison. So the observations do lie within the model ensemble, which is reassuring. And we can now take our 4 Gaussian processes. Oh, well, we can train our Gaussian processes and create our emulator. So before we go ahead and use our emulator, we want to check that it is accurate. So this has been done by a series of methods in our paper, but we're just going to quickly take a look at the take a look at the emulator error here and compare that to the model error. So it is really difficult to quantify a model error in a complex model, and often things like expert judgment have been used. But here we've just created a lower bound for the model error by looking at the effect that the invariant parameters can have on the output. We take the standard deviation in the output for the 90 simulations where only the invariant parameters were varied as the invariant parameter error. So this invariant parameter error does not include many types of errors, such as those involved in model transport. So this is a minimum for the model error. But as we can see in this plot, the invariant parameter error shown in blue, so again, these are the 4 emulators that we had on the previous slide, is much larger than the emulator error, which is shown in green, for all 4 of our outputs. So the emulator error contribution to the total error, which is shown in black, is actually quite small. So for a lot of other analyses, you will also have an error from how well you can expect the model to match observations. And in this system, this error is about the same size as the invariant parameter error. So this means that this invariant parameter error is a substantial source of previously unconsidered uncertainty. So we can now go ahead and have a look at how well the Gaussian process is performing by comparing its ability to emulate the model to multiple linear regression, which assumes that the relationship between inputs and outputs is linear and that the parameters do not interact, unlike the Gaussian process. So we can get the Gaussian process and multiple linear regression to predict the model output for the test data set, and then take a look at the differences between the method and the model, which is shown here for mole fraction on the left-hand side and delta value on the right-hand side. So the Gaussian process, which is shown in gray, has a much smaller range of residuals, especially for the mole fraction. And you can see the multiple linear regression residuals, which are shown in orange. There are actually lots of these runs that are tens of ppb off, and on the delta value side, there's quite a lot that are over 0.2 per mil up to 0.4 per mil. So it is possible to reduce multiple linear regression residuals by transforming it and taking like the log of the hydroxyl radical instead of just a linear representation, which is shown in blue here, but it's still performing significantly worse than the Gaussian process. So by assuming that the relationship between sinks and mole fraction is linear and that parameters don't interact, as several previous studies have done, is potentially an important source of error. Hopefully you're happy that the emulator is useful. So let's go ahead and try and use it. So in our paper, we carried out a variance-based sensitivity analysis, which typically requires millions of simulations. And this type of sensitivity analysis does allow a full exploration of parameter space and accounts for parameter interactions. So an example of a parameter interaction is the hydroxyl radical loss and any source interacting to affect the global mean mole fraction. So like a lower hydroxyl radical concentration would cause a greater mole fraction increase for the same increase in emissions than if the hydroxyl radical concentration was higher. So in this variance-based sensitivity analysis, we use sensitivity indices in order to describe the sensitivity. So the first order sensitivity index is just the proportion of the variance in the output that can be attributed to a single parameter. And the total effect sensitivity index is the proportion of the output variance that can be explained by a single parameter and its interactions with other parameters. So if you have a really large first order sensitivity index, then reducing the range of this parameter is going to greatly reduce the range of the output. But a parameter can still have a large effect on the output and a small first order sensitivity index by having parameter interactions. So by carrying out this sensitivity analysis, we can see what sources and sinks would be most beneficial to reduce uncertainty in with more research in order to learn more about methane budget. So here we've just plotted up the first order sensitivity indices for 6 outputs. So on the left-hand side, there's the mole fractions, and on the right-hand side is the delta values. On the top row, we have global mean, and on the middle row is intensity difference, and the bottom row shows the trend. So on the x-axis is just each of the 28 parameters that got varied, and on the y is the percentage of the output variance caused by varying that parameter alone. So for the mole fraction, the hydroxyl radical is really quite dominant here, which is hardly surprising given that it is the largest single term in the methane budget and also has a really large uncertainty. It doesn't really show up in the intense effect difference, but that's more because we've assumed OH parity between hemispheres. So had that not been assumed, that probably would be showing up strongly there. But we also see things like freshwater emissions showing up, and a few others, but freshwater is particularly interesting given that it's often left out of studies altogether. And then on the delta value, so on the right-hand side, we can see that lots of different terms contribute, including many that the mole fraction is insensitive to. So it is a useful complementary measurement to go alongside the mole fraction. And we can see some of the terms featuring prominently here. So chlorine, which is sometimes left out, freshwater, again, that's sometimes left out of methane studies. And what we can see quite clearly is that there's actually quite a strong dependence on the initial conditions. So that's the bars towards the right-hand side of this plot. So the output's actually really dependent on the starting point. So that's something we need to bear in mind when looking at these delta values. So just briefly, these are the parameter interactions from the sensitivity study. So the plots are in the same order as the last slide. So mole fractions on your left-hand side, the delta value on the right, and top row is the global mean, and middle row is the intense effect difference with the trend on the bottom row. The interactions across all parameters account for 12% of the output variance in the delta value intense effect difference, but at most 2% for the other 5 outputs. So actually, in terms of a sensitivity analysis, we can essentially consider the effects of the parameters independently. However, because we're trying to build like a really accurate emulator, these parameter interactions do need to be considered when we are building an emulator because we're trying to predict really small quantities with high accuracy. So things like the intensity difference and the trend are obviously quite small quantities. So just going to wrap it up here. So I think the main thing to remember is that actually the Gaussian processes emulators are really useful, and it's allowed us to reproduce complicated model output, but with a much shorter runtime, which allows us to carry out a larger range of analyses than could be carried out on the complicated model by itself. We also saw that simpler techniques like multiple linear regression just don't perform adequately due to the non-linearities and parameter interactions. And by conducting a variance-based sensitivity analysis, we've shown that sources and losses, so things like fresh water and chlorine, which are quite often left out of studies, maybe should be included, as well as having a look at how useful delta values are to us as a complementary measurement of the mole fraction and how sensitive they are to the initial conditions. And whilst they are complementary because they are sensitive to many parameters, some of those parameters are only needed to be included because we have included a delta value and don't actually tell us about the methane budget itself. So these are all important things to bear in mind, and I think I'll wrap it up and leave it there. Happy to take any questions if anyone has any. Thank you.
Thank you very much, Angharad. Really interesting talk. So are there any questions? Please put them in the chat. I'll ask one in the meantime. One of your figures showed the importance of the chlorine methane sink. I think for the delta C13. Was that expected? And does it refer to methane loss by chlorine in the troposphere and the stratosphere, or is it just a tropospheric term?
Yeah, I think it is broadly expected. I mean, there's been quite a lot of work on chlorine recently, especially of its impact on delta values. So whilst it is quite a minor term in terms of the methane budget, it's obviously got quite a large ability to change delta values. So when I was referring to chlorine in this paper, it was just a tropospheric one, but we have also included a stratospheric sink, which will have chlorine in it, although we haven't separated that out in the stratosphere.
I see. Okay. The other question I had as well was, I mean, I can see this is really useful stuff. I mean, I wonder if you repeated this in a kind of multi-model framework. I guess not, but would you expect to see similar associations between the different models, or would we find something quite different?
Yeah, so we have only done it in Mozart. It would be reasonably easy to extend to other models. The problem is only that you have to generate a training data set in the first place, which is by far the most computationally expensive thing. So yeah, that's kind of your limitation really, as to like how many models you're going to put this on, is how much time do you have to generate training data sets, or if you have stuff already. I'd probably expect to find pretty similar things for these broad categories. You would see differences, I guess, particularly in things like delta values potentially, where it's like a bit more, I don't know, they're quite sensitive to small changes, aren't they?
Yeah.
So I think you'd broadly see the same kind of picture. Certainly on the large scale, there'd be some small differences. But yeah, you'd be very constrained by how much time you have.
Yeah, I guess getting other modelers to sign up to doing those simulations might not be straightforward, but okay. So I don't see any questions, so I think we'll move on. Thanks very much for that talk again. So our last speaker of the session is Matt Amos from Lancaster University. Thanks, Matt, over to you.
Hi, I'll just figure out how to share my screen again. I had a tech issue this morning, so if anything doesn't work, please forgive me temporarily. Can we see slides?
Not yet. I can see. Yeah,
Excellent. There we go. Cool. I didn't even practice, so that's awful. Yeah, so hi everyone. Thanks for inviting me to round off the session today. It's been really great to listen to everyone talking, all of the exciting work that's going on in the space between atmospheric science, atmospheric chemistry, bits of climate science, statistics and machine learning. Today, I wanted to talk about some recent work, which is a collaboration here in Lancaster, which is building Bayesian models, which help us combine output from climate models or chemistry climate models with observations to allow us to make better projections out towards the end of the century. I promise there won't be, I don't think there's any maths in this talk actually, but if anyone wants any maths detail, you can come and find me afterwards because there's a lot of maths underlying this. And I'll just say thanks to the two co-authors who've both now left Lancaster Uni and academia into the big world of industry. Paul, who I'm sure many of you know, and Tom, who is a statistician and brought along a lot of the statistical rigor to this work. So to put the next 20 minutes, 15, 20 minutes in context, I thought I would just introduce the space in which I work. So I work for a project called Disney, Data Science of the Natural Environment, which tries to put environmental science and environmental challenges in front of statisticians and domain experts. And this sounds wonderful, but in practice, it often means you spend many confused hours deciphering each other's technical terms, such as the difference between physical models and stats models, and getting hung up on that language. And also what maths people do when they run out of Greek letters. But the outcome of this is a really mixed environment, which can be great because we can really get down to creating data models and stats models that are really highly customized and suited to a particular environmental problem. We often find there's an environmental challenge that needs solving and a model literally doesn't exist, so we go and build a new model for that. So I call myself an environmental data scientist, and that encompasses all of those above terms, but very rarely I get let out of the office and I get allowed to go and do some real air quality science as well. I should add as well, and this is a shameless plug, I'm currently looking for jobs, either academic or industry. So let me know if you have anything going, and I'd be very happy to chat about that. So what I wanted to talk about is thinking about how we combine model output from these large ensembles, CMIP6, CCMI. And I say model here, model is any sort of numerical model. So it could also be a hydrological model or any chemical transport model. And how we combine those sets of models with observations and expert knowledge. And we might want to do this like Kai-Lang Chang's work, where they've fused together some TOR data with model output to create this fused record. Some previous work of mine using Bayesian neural networks to infill gaps in data. And maybe we just want to get rid of chemistry models altogether, and we just want to build a pure data model which ingests fields or predictions, ingests fields or variables and gives us predictions, and we're not even using any numerical models here. We also might want to find biases in climate models where schemes are going wrong or some parameterization is wrong. And so if we formulate all of those ideas in a machine learning sense, what we're trying to do is we're trying to combine multiple streams of information in order to make more informed inference about the world or about data. And in theory, these are all regression problems. So we could replace that arrow in the middle of the slide with a whole host of machine learning models, such as some we've heard about today, deep neural networks, random forests, or as I'm going to focus on a little bit today, Gaussian processes. Because we're often producing output that has important consequences, say, we might be using this for the World Meteorological Organization's ozone assessment report, or maybe the likelihood that CFC emissions have originated from this particular region. We need to do all of this modeling within a rigorous statistical framework to capture the uncertainty. And so that's why I've added the Bayesian in here, because that allows us to do that. So I thought I'd just spend a couple of, well, maybe 1 or 2 minutes saying why we'd want to be Bayesian in the first place, because when we build machine learning models, if we make them Bayesian, they often become more complex in how we write them, but also when we're computing, it becomes more expensive. So a simple explanation and an example can be considering this plot. Which of these models is better? Which is more informative? Which one do we want to trust more? And of course, it's a really silly question because we can't tell if we don't know what the uncertainty is. And though both Bayesian and non-Bayesian models can give us uncertainties, Bayesian ones typically provide us with much more principled and rigorous ways to quantify and propagate any uncertainty along models. Second motivation of why we might want to build a Bayesian model is it allows us to include prior understanding into this data model we're building. That could be some sort of domain-specific knowledge. Say we're modeling on something on a sphere. We're not going to unwrap the map to have latitude and longitude, because a point at the far left end and the far right end, the machine learning model will think are different. So we want to kind of model it on that sphere instead. If we're modeling air quality, we might use a lot of data sets to model it and get that inference, but we're also going to want to include some knowledge such as the lifetime of certain species, or maybe how, like our prior understanding about how pollutants vary spatially. And so as we train or fit a Bayesian model, we see some evidence in that light green, and we have our prior belief. And a Bayesian model kind of combines the best of both worlds there and gives us this posterior, which is our final understanding of the system, which is a combination of the prior and the evidence the model has seen. So moving on to the problem at hand, and this is what the rest of the talk is going to be about, it's all about combining models and observations to make better climate projections out into the future. To make estimates of future change, we typically use output from multiple models. We don't just use one because it might be flawed. We use a whole combination. And this idea of ensembling models to produce more accurate projections isn't just used in climate science. We use it across statistics. Maybe the idea of bagging, or Lily was talking about XGBoost. That's another kind of ensembling method where we're just using lots of things, lots of methods in order to get a better prediction. It's a sort of strength in numbers approach. And it also, as you can see here, it allows us to constrain the uncertainty. On this little schematic, there are, say, 7 climate models in red, and they all have different predictions because of their design, maybe how they're influenced by interannual variability and the chaos in the atmospheric system. So in theory, that black line, which is an ensemble average, is going to be a better predictor of climate change than any single model themselves. Most commonly, though times are changing a little bit, people tend to use the multi-model average, which just means I take a Euclidean mean across all of those models, and I take the standard deviation across them to give me my final projection. So that multi-model mean is where we're including all the models equally. It's also called model democracy, one model, one vote. But we have to be a little bit careful when we're constructing these ensembles, because a multi-model mean ensemble assumes that all models are equally good and they're all independent from one another. And these two plots kind of show us why that's not necessarily true. So this plot on the right-hand side, it's from an old paper now, but it still stands. I squared here is a metric which quantifies how good a climate model is. And all of the colored dots are different climate models. So you can see that there's this huge variation in the skill of a climate model, aka how well can it represent climate dynamics, how well does it match observations. And so that plot really shows us that climate models aren't necessarily equal. Some will model certain regions better. Some will model, say, spring better than summer. And so we kind of want to include that information into how we build ensembles. The plot on the left-hand side is a kind of family tree of CMIP5, and it shows us how different models are related to one another. And this happens because people borrow code, model components, plug them into their own model. But statistically, this creates a problem for us because it's saying that these models aren't independent from one another. So say we've got two really similar models, they're going to count double in the ensemble we produce if we use a multi-model mean. So what I'm trying to say is a multi-model mean approach needs to be treated with caution because it can quite easily become biased and underconfident. But on the flip side, admittedly, it's really efficient and easy to calculate. You can often do it in one line of code, and so therefore it's a well-used tool. So I'm going to introduce our way of doing things that we formulated, and it's a fully Bayesian approach to climate model projections, which we hope will be used to produce more rigorous and accurate projections. There's 3 steps to it, and I'm just going to walk through the 3 steps. We start on the left-hand side, and you can see we've got on those leftmost plots, there are 3 models, and we've got about 10 to 25 realizations from each model. So the realizations are just running the model again with slightly different initial conditions, and the chaos in the system means that we get quite different projections. Firstly, we want to emulate those models, much like we heard about in the last talk, and that will allow us to estimate the likely range of outputs for that model before weighting the models against the observations to determine a metric of skill, which you can see in the 3rd plots along the little black dots for observations. And then lastly, we want to aggregate all this information into a final projection. So essentially it's output from multiple models plus some observation, and then we're going to combine all of that and we're going to create a final single projection. Step 1 is emulation. I should add this is a little bit different to the emulation we just heard about. It's nowhere near as computationally expensive because we're not trying to emulate all the different parameters within the model. We're just saying, under this scenario, what might this model produce? And so we're capturing the interannual variability, the subdecadal variability into the uncertainty of that model. And that's what you can see in the shading on the right-hand side, which shows to 1 standard deviation, what is the probability of that model producing a realization which lies within that envelope. So the emulation of the climate models gives us a probability distribution which we can compare against observations. I won't go into the details here, but I'm very happy to talk about it another time. We perform this using a sparse hierarchical Gaussian process, which is a model we developed specifically for this. And it's a model which is able to extract underlying latent signals from multiple streams of data. So say we had 5 adjacent air quality sensors, you could plug those 5 time series into this model and it would be able to model all of them individually, but it would be able to tell you what signal is shared by all of them. So yeah, I'm happy to talk about that offline, or if anyone's coming to the NeurIPS climate change workshop tomorrow, I'll also be there. So now we've emulated these models, we want to compare them against observations. And so on these plots, you can see the little black dots are a series of observations. And there are many sensible ways to score distributions against observations throughout the maths literature, and they're called proper scoring metrics. Examples include things like kernel-Stein discrepancy, continuous rank probability score. And all they do is they allow us to say essentially how good is a model? Do the observations lie within the probability distribution of that model? And they also allow us to find out which models are really similar to each other, which helps us kind of pick apart the problem of model dependency I was talking about a few slides ago. So we use these weights because we want to trust models which are closer to the truth or are more likely to give us a representative. projection. So here you can see the green model at the top. All of the observations, or nearly all of the observations, fall within one standard deviation of that model's projections, and therefore we're going to weight it the highest. And then lastly, we need to bring all of this information together. So we've got emulated climate models, and we've got a weight for each climate model, which tells us essentially how good it is and how independent it is. And so to aggregate all this information, we'll use what's called a Wasserstein-Barry center, which has it sounds complicated, but it has a wonderfully intuitive explanation. So imagine here we've got these blue and green regions, and they're hills, or they're piles of dirt. And we want to combine both of those piles into a single pile whilst minimizing the amount of shoveling and the amount of work we have to do. So the Wasserstein-Barry center will tell us where we need to put that soil or that dirt to combine them with the minimum amount of effort. And so that's what the red region is here. It's important to notice as well, the orange region here is a Euclidean mean, what you'd get if you did some sort of multi-model mean. And you actually get quite a different projection. And it's because the Euclidean mean is not really designed to propagate uncertainty. And so by using a Wasserstein-Barry center, which is a probabilistic method, we actually get quite a different answer. So basically, a Wasserstein-Barry center will give us the average distribution between multiple distributions from climate models. And so you can see this here. These are the same emulated models. If we take a slice through that black line, we end up with these three Gaussian distributions on the right-hand side. And so at every point in time, so we've got time along the x-axis here, we want to calculate all of the distributions of the models. And that is telling us the likelihood of the model making a prediction or a projection within that boundary. And then we want to take all of that information and combine it to one single Barry center, which, as I said before, is kind of the average probability from all of those models. But I said we were going to weight the models because some are better than others, some are more representative. Say we're just looking in the Northern Hemisphere. Northern Hemisphere produced models tend to be better at modeling the Northern Hemisphere, so maybe we'd find those were better. But here we've got different distributions in red, and then the Barry center, the average distribution, is in blue. And you can see if, say, we weight the leftmost distribution highest, that Barry center shifts over to the left because we're kind of favoring that model over the other models. So that was a really quick run through methods which are really hiding quite a lot of maths underneath, but hopefully some of the ideas are intuitive. And so this is these are some of the results. This is a probabilistic projection of southern polar springtime ozone relative to about 1980 levels. So this is a key metric for monitoring the ozone hole. And I should add all of these projections are produced from CMIP6 class models. And here the shading shows 68%, 95%, and 99% credible intervals. On the left, you can see the historic period compared to observations. And so over the historic period, we've emulated all the models, we've compared them to the observations, we've created a weight, and then we've pushed that weight into the forecast models. So say CSM got a score of 0.25 in the past. In the future, it's also going to get a score of 0.25 when we create our final probabilistic projection. And you might ask, how sensible is that? Are we allowed to say that because a model was good in the past, is it good in the future? And we can do a lot of tests like cross-validation, perfect model tests, and you find out that is normally a pretty sensible assumption to make. We can say that because a model was good in the past, it is so again good again in the future. You might notice these are really spiky. You might expect the distributions to be way smoother. And it's because there are only 5 models in here. The downside of methods like this is because we're trying to quantify uncertainty, we need model outputs where they've run multiple realizations. If a model just runs one realization, we can't begin to quantify what the uncertainty of that model is. But essentially, using those models, we've been able to project out to 2100, though I think it only shows 2060 in here, as an estimate of, say, when the ozone hole is going to recover. Similarly, we've done the same in a climate sense for global surface temperature. Again, these are two different scenarios, SSP 245 and SSP 370. And it's just showing what the projections under this probabilistic framework look like. Now you can see them in orange. You'll notice they're a lot narrower. And there's some nuance here because in CMIP6, the range of models is enormously broad. Using this method, you can begin to discount a lot of the kind of more extreme models quite quickly, and you end up with a narrower bound. It also, there's a slight other bit of nuance to it, which is that the standard deviation or the shading you can see on the projections into the future here is not saying this is the range of 10 models. Instead, it is saying this is the likely interannual variability for the model. So given all of that information we know, we would expect the future of climate, given that there's going to be emissions such, according to SSP 245, we would expect that to lie within that orange shading. A couple of reflections on the work at the moment, because it's currently a work in progress. I'm always very interested to hear what people who run models think of things like this. Multi-model ensembles are of huge importance because not least do they go and eventually go to influence policy. They tell us more about the world. They tell us about risk mitigation, how we're going to adapt to changes and different things, or how we might need to. And a lot of that is all to do with risk and uncertainty. And the reason for creating this Bayesian framework is because it allows us to quantify that uncertainty in a much more rigorous way than what exists currently. And that uncertainty is important so we can make these kind of risk-dependent decisions and strategies, etc. The model as I introduced it was this three-step process, but because it's Bayesian, you can plug in and you can pull out different sections of that model as you want. Say you don't want to weight the models, you don't need to. You could just do a probabilistic average of all the models. A bit like a multi-model mean, but you'd still get quite different answers to that. And finally, I was just going to briefly reflect on working in the very middle space between environmental science and statistics. For anyone who's thinking of getting involved in it or is finding it tricky to become part of that kind of exciting community. And it's very exciting because you get to work in two fields. You get to push the boundaries and innovate in both places. But then it's also simultaneously exhausting because you're trying to keep up with two sets of literature, and the speed at which the machine learning community moves at the kind of cutting edge is immensely fast. And it's really hard to keep track of that. But say for this work, not only did we design like a new framework for the environmental science community, along the way, we had to produce a new machine learning model because there was nothing off the shelf that would work for us. I would say as well, a lot of machine learning people I speak to are dying to do some sort of environmental or climate work, but they just don't know where to get started. And I know there are a lot of projects, including WeatherBench, Climate Bench and AQ Bench, to kind of get easily accessible data out there to people. But if you've ever thought about yeah, like trying something new. My experience is that most machine learning people and stats people are really excited to talk about what they've done and apply it to a problem. Way too often do I hear in our office, oh, I've made this really cool machine learning model, but I have absolutely no idea what to do with it. There are loads of these things around. I suppose as a final point as well, for those who teach and lecture in universities, I think coding needs to be taught to undergraduates. I think it's a really important skill to get into this domain. And I know at least at our university, I don't think people are really taught coding until master's level. But that was just an aside for keeping the community going in the future. I'll leave it there. Very happy to take any questions online or offline, or talk about this in general. I'll quickly add that all of the plots and all of the work here today is all wrapped up within a Python package, which is still under development, but is public, and anyone can go and play with it. But essentially, as you can see in the top right section of code, that is all the code you need to produce some of those plots and things we've seen today. We've tried to wrap it up in a way that interfaces with common Python packages such that people can really get using this method. We don't want there to be a massive barrier to entry. So you can go and find out about that, and also about any of the sparse hierarchical Gaussian process stuff, simply because I think that's a very promising model for finding shared functionality between models, data sets, different streams of data. So yeah, thank you so much for listening. I hope everyone enjoys their evenings, and I'm very happy to take any questions.
Lovely, thanks, Matt. Really interesting talk. Questions for Matt? Matt, on your point about coding at the end there, it's a good one. I think it differs across departments and degrees and universities. You know, a lot of undergrad dissertations might be Excel based. It is challenging, I think, to introduce coding at undergrad level, but I agree with you that it would be massively beneficial. I do agree. Yep.
Yeah, before we all get our jobs stolen by the ChatGPT bot.
Yeah. A quick question for me before I go to the ones in the chat, and forgive me if you did mention this, but does, in evaluating the metrics to test how good the models are doing against the OBS, which inform the weighting, does observational error factor in somewhere in that?
Yeah, so these models we build, they are formed of what we call an aleatoric and an epistemic uncertainty, where the epistemic uncertainty is the uncertainty of the model. Is the model modeling what it can efficiently? Whereas the aleatoric uncertainty is that pure, what is the uncertainty in our data here? And so that is factored in, either by specifying it from a data set or trying to calculate that on the fly.
Okay.
But yeah.
Great. Questions in the chat. Did I see one? I think I did. No, I think I was actually looking at a comment from earlier. Beg your pardon. Okay, so if there are any questions for Matt, pop them in the chat, or else. Matt, you said there was a workshop coming up as well this week?
Yeah, I don't know if many people are going. It's tomorrow is the NeurIPS Climate Change AI workshop. And I know there's a group of people meeting in Cambridge just more broadly for NeurIPS, but it's a virtual conference. Well, the workshop is virtual, and there's a lot of very exciting talks in the kind of ML, climate, atmospheric science domain.
Yeah, okay, great. I was looking at the EGU schedule earlier as well. I think there's some for next year. I think there's some interesting sessions there too.
Yeah,
certainly lots going on in this field, isn't there? Okay, well, I guess that brings us to the end. Just to say thanks again to all the speakers, both this afternoon and from the morning session. It's been fascinating hearing about this research. Paul's about still. Any further comments, Paul?
No, just to echo your thanks and look forward to seeing this on YouTube when it's been processed.
Indeed, yeah. So thanks everyone. Keep in touch and hopefully see you all in person soon.
Thanks all.
Bye-bye.